feedback out of am I visible and audible? Because there was some.
Yes, sir. Yes, sir. You are reconnected. You're visible. You are audible.
There was some breakage. My screen is visible. Okay?
Yes, sir. Screen is being shared.
Fine. So I was talking about descriptive and inferential statistics. So for example, if you are designing, let us say, a feedback form for the class that you have recently conducted, and you ask a question like whether the course was completed on time. This question is a binary question, so answer is of course in yes or no. But instead, if you give a student to mark this on a scale of 5 as best and 1 as the worst, or vice versa, and so that is not very reflective of what we want to know. Okay, because it's not a qualitative assessment; it's a binary assessment. So the descriptive statistics plays very important role over here. So you have to assign a binary number as yes or no in putting the answer for this kind of survey. Second, if you are giving some sort of qualitative assessment, say you are asking that whether the teacher was effective enough in communicating the thoughts and ideas in the class. So it can be rated on a scale of 5 to 1. So 5 most effective, and 1 as as the least effective. So this can be actually part of a descriptive statistics. So how do you collect and present the data, and that data should be reflective of any analysis that we are further going to produce. Now, this is known as low-level statistics. The second level of statistics is inferential statistics. So we try to draw conclusions and make decisions, concerning a population based upon sample data. What is population? Population is the all sample, available for any kind of experimentation. So that is inferential analysis. So rather, this is basically data analysis. So I will just define very briefly what is a population. Population is the set of all items or all or individuals of interest. So all likely voters in the next election, for example, which is very popular data analytic experiment. All parts produced by a factory, all sales received in a particular month, year, or whatever. what is a sample? Sorry, am I audible?
Yes, sir. It was something like it was my mistake. Some participant might have unmuted.
Okay, no
Okay.
problem.
Please continue,
And
sir.
what is a sample? Sample is a subset of the population. Okay. Now, so we are going to here focus upon our whole, analysis on the samples, how to collect sample, and what is the role of distribution of various samples, how many samples may be there. I give you an example which I often use in my class. That suppose the student gets, marks in a class test or end semester examination or wherever. Now, the sample size may be 100, 200, whatever is the size of the class. Based upon that, we have to analyze that where is the mean, what is the variance, and if the distribution is not normal, I hope you all understand normal distribution. So if the distribution is not normal, then how can we actually use techniques to make it a normal distribution so that we can draw some sort of inference? So that particular aspect we are going to discuss today. Now the question is, why samples? Now the answer is very obvious, but I'll repeat. See, sampling is very less time consuming because you work on the subset of the data, not on the entire population. It is less costly, and it is possible through these statistical tools and methods to get the high precision answers based upon these samples. And research process sometimes is very destructive. The sample can save the product, right? So when you go on doing analysis on each samples, then this can destruct the data, or sometimes can be very time consuming. So you can actually save the product or the outcome that you are going to get. If assessing the population is impossible, then sampling is the only option. Suppose there is 125 crore people, and assessing all 125 crore population will not be possible in, let us say, 3 months of time. Then sampling is the only answer, and there is no other way you can proceed. Now, there are two kinds of samplings that we do. One is random sampling, and another is a non-random sampling. And what is random sampling? Every unit of the population has the same probability of being included in the sample. So suppose you are actually trying to get the sample, out of the subset, and so every item which is there at the part of population has the same probability that it will be included in the sample. This might be true, this might not be true in particular observation, right? But random sampling is done where this is true. Say, for example, there are two-party system in a country. Then the answer is that if assuming that everybody is participating in the voting process, then the fellow will vote for party A or party B. There is nothing like party C. There is and there is nothing like not voting for either of the party. So but in context of India, for example, certain constituencies are reserved. So the likely chance of participation of all the samples in every constituency is not the same, because there are different criteria for predicting or placing the candidates in a particular sample space. So then we have to actually categorize the entire population into subpopulation, and then in those subpopulations we have to apply sampling. We'll see some examples related to that. Chance mechanism is used in selection process, right? So of course there is a probability involved. Eliminates bias in the selection process. So random sampling can eliminate, because when you're doing something randomly, then there is nothing like skewness. Skewness means you can't go to the extreme low or extreme high, because randomness will ensure that data are selected based upon a random number, and therefore there is an equally likely chance that every data can be selected. So biasness can be reduced if the sample size is pretty large. And this is also known as probability sampling, of course, as the name suggests. Then there is a non-random sampling. Non-random sampling is every unit of the population does not have the same probability of included into the sample, as I talked earlier. So in contrast to that, now this is open to the selection bias. How do you pick up the sample, that biasing may be reflected over here. And it is not appropriate data collection method for most statistical methods. So it is known as non-probability sampling, which is least used in very extreme possibilities. You'll see one or two examples where non-random sampling is desired. Otherwise, in most of the cases, random sampling is being used. Okay. So random sampling techniques are also classified into number of parts or number of types, you can say. One is simple random sample. Another is a stratified random sample, where proportionate or disproportionate samples are taken. Say, for example, if you are conducting a survey across the country, then what should be the sample size in a state like UP and what should be the sample size in a state like Manipur? Now, Manipur is a very small state as far as population is concerned. So we take the proportionate, data from these samples because of the non-uniform distribution of the population in various states. So this is stratified random sampling. Systematic random sampling we'll talk about in short while, and cluster or area-wise sampling. So we can say that let us have a survey in northeast area, let us have a survey in southward, and so on. So for example, if you are trying to predict some data in garment industry, then the garments which are preferred in northeastern part of the country may be different size-wise, color-wise, choice-wise, and the garments preferred in the western part of the country, Maharashtra, Gujarat, may be entirely different. So in that case, we have to go for cluster or area-wise sampling. And this is true in terms of diseases also. Some of the diseases are more, in numbers and intensive in one part of the world, and some may not be there in the another part of the world. Then we need cluster or area-wise sampling to draw some conclusion. Okay, we'll see these techniques, in greater detail. Then simple random samples are every object in the population has an equal chance. So the first one is the most simple, random sampling technique. So every object has an equal chance of being selected, and objects are selected independently. So they may be randomly selected. Samples can be obtained from a table of random numbers or computer random number generators. And simple random sample is an idea against ideal against which other sample methods are compared. So simple random method is the most fundamental and basic method, and with this, we can compare the other methods also. So, for example, there is a population frame, and we have taken 20 states, for example, and in these 20 states, we have to select, for some analysis, let us say 4 or 5 states. So, how to select 4 or 5 states for doing some sort of analysis out of 20? So, our sample size is 20. Our population size is 20, and we have to go for a sample size of 4. So which 4? So we can have a random number. Random numbers are like, we are having 9, 9, 4, 3, 7. And this way, we can actually have 1 to 20, because there are numbers in 2 digits. We can start here from, let us say, 99. So 99 is no number there. Then there is 43. 43 is no number there. 78 is no number there. 79 is no number there, 61 is no number, 45, 73, 73, 75, 52, 97, 96, and this way we can go on. And finally, we may come to a point where we get number like 16 in red color, you see. So this 16 appears over here, and we can pick the first state as Tamil Nadu because 16 appears. So that's a pure randomness through which we are picking up the numbers. Because the states are numbered in 2 digits from 1 to 20. There may be more numbers, states, so it's just an example. And we can pick up the numbers which are matching in a random way. So first number is 16, another is 18, another is 01, another is 27, and this way we can pick up various states like that, as many as we desire. Okay, so this is how computer also generate random numbers, and we may do it through this manual process also. So this manual process was just an illustration or example, but nonetheless, you can have a computer program, and in programming languages like Python or R, you have a random number generator in place which takes all these statistical consideration with the appropriate. Second, types of random sampling is stratified random sampling. And what is stratified random sampling? Population is divided into non-overlapping subpopulations called stratas. Okay, a random sample is selected from each strata. So, for example, we want to conduct a survey, UP, Bihar, or whatever. This way we divide. So, we will divide the country into 4 parts. Let us say northeast, northwest, southeast, southwest. This way we will divide the whole country into number of stratas, and from these zones we can actually collect. So, for example, if you are predicting that who is going to be the next prime minister, and let us divide the whole country into 10 zones, 10 stratas, and we can have a survey, and those survey data can be collected out of those stratas separately, and then we can have some sort of predictive mechanism in place. So random sample is selected from each strata, and potential for reducing sampling error. So if you decide this strata, so the variance in the strata should be as less as possible. So that's the most important thing. And at the same time, the strata should be non-overlapping. So it should not happen like, 2 zones are included overlappingly each other. Otherwise, this may generate some sort of error. And proportionate, is the percentage of the sample taken from each stratum is the population of the percentage. I talked about that earlier. Sometimes disproportionate, samples are also taken. For example, we will like to gauge more samples from a state like Manipur than samples from UP. So suppose we know that the data is less likely to have much variance in a particular state. So you select less samples, then also it works. But if the data is going to have a larger variance, then we have to take more number of samples from that state. So for example, UP is a bigger state where variance is very large. Some area may go for one political party, another area, even the adjacent constituency may go to the another political party. So here sample size is required to be very, very large, not just reflective of the population. But if the entire state is going to be swept away by just one party, then a simple samples may be taken. So this assessment has to be done descriptively prior deciding stratified, proportionate or disproportionate sample. So stratified random sample. So for example, we are trying to decide the population of FM radio listeners. So we have stratified the data as the age group which is 20 to 30 years old, age group which is 30 to 40 years old, age group which is 40 to 50 years old. So they all are homogeneous within. So homogeneous means there's no difference as far as properties are concerned. The kind of music they listen, the kind of programs on FM they listen. So they are homogeneous. But so there is a difference as far as the entire population is concerned. So heterogeneity exists among the samples, but the data within sample is homogeneous. So in this case, stratified random sampling can be used. I gave example of of election surveys and all. So this kind of samples may also be collected. Third sampling, which we have not talked earlier, was a systematic sampling. Systematic sampling is convenient and relatively easy to administer. Okay, so population elements are often ordered in sequence or at least conceptually. So what we do is the first sample is selected randomly from first K population elements, and then after sample elements are selected at a constant interval. So for example, there is a large population of 1000 population data. Out of 1000 data, we select that we are going to take a number as 50. So we take the 50th sample as the first data, then next 50th, that is 101st data as the second sample, next 50th sample as the third data, and this way we can go on selecting the sample. So it's not that random, but it's a systematic sampling. Okay, so we have decided upon K. So N is the sample size, how many samples we want to take. N is the population, and we take the ratio, we get K, and K is the selection interval. So this is a systematic sampling. And the systematic sampling may be, example, suppose we want to do audit of various receipts which have been collected by the account section in a year. So we will say that we will take 5 receipts from the month of January, 5 receipts from the month of February, and this way In all 12 months, we are going to take 60 receipts, and we will audit these 60 receipts to see that every month things were or the expenses were performed properly or not. So this is systematic sampling, which is also used in many cases. So purchase order for previous physical years are supposed to be realized as 1 to 10,000. So suppose 10,000 purchase orders have been issued by your institute, and sample of 50 purchase orders we want to see. So which 50? So 1000 divided by 50 comes out as 200. So first sample element is selected from the 200 purchases. So first 200 purchases, we will select any one. Next 200, we will select any one, and so forth. So 245, 445, 645. Assume that 45th purchase order was selected from the every sample, right? So you see, they all are spaced at 200, and 45th is the index number we have decided. And this way we can actually, and this 45, this may be 45, 95, and so on and so forth. So this is systematic sampling. Cluster sampling. Cluster sampling is population is divided into non-overlapping cluster of areas, whereas all clusters are considered as independent population. So they are not dependent on anyone. So they are a smaller population. So subset of clusters is selected randomly for a sample. And if the number of elements in the subset of clusters is larger than the desired value of n, then the clusters may be subdivided to form a new set of clusters and subjected to a random selection process. Like states in India, is one of the best example of cluster sampling to see that what is the impact of a scheme which is rolled by government of India, right? So we may see, dividing the entire country in the cluster of states, and we can see the performance of the states out of some index and can actually conclude. So advantage of cluster sampling is more convenient for geographically dispersed population. Impact of a scheme in Kerala may be different than the impact of a scheme in Bihar, right? So, for example, agriculture reforms may have good impact in some of the states, but may have a bad impact in some other states also. So, where there is this kind of dispersion, which is very true in case of Indian data, cluster sampling is very helpful, and which is used most of the time. Reduce travel cost to contact sample elements, because you don't have to go for the entire population. The simplified administration of the survey, unavailability of the sampling from frame prohibits using random sampling. So it's not that random, we are actually having subpopulations, and therefore it's more accurate and precise. This advantage is statistically less efficient when the cluster elements are similar. If there is less differential, then there is a wastage of cost and money. Cost and problems of statistical analysis are greater than the simple random sampling. So of course, simple random sampling just selects randomly any data. Here you have to do it cluster wise. So the cost is high and the analysis is much more complex. Okay. Now, one of the another kind of sampling where randomness or probability is not used is a non-random sampling. And non-random sampling is is very rarely used, but it's very convenient because we just select anything as non-random in a non-random fashion. So there is no probability distribution. That's the most important point. It's like a non-deterministic finite automata. You just choose one of the option and that's it. So what is the basis on which you choose sample? Convenience. So it's very inconvenient to go to Northeast to collect the data. So I will select, as per my convenience. Judgment sampling, some manager or some higher authority have said that, just collect these data and do the analysis. That is known as judgment sampling. Quota sampling. Quota sampling is I will take, 10% of the elements from general category candidates, 5% of the data from SC/ST candidates, 5% from OBC, and that's a quota sampling. So we have actually classified the entire population based upon some criteria, and we are taking samples from all, these criteria, populations. So that's quota sampling. It might be reflective of some property, but it might not reflective of the all property. And snowball sampling is based upon the previous experience. So somebody else has done sampling, and we go by referral. So somebody has said that yes, I was in Kerala, and Kerala has this trend or this data. You just take it, and I have taken it as it is. So that's a snowball sampling. So data is not collected, but snowballing has been done. So in most of the artificial intelligence and machine learning analysis, people take data from the websites which are available, which might be contextual for a particular population, but they do analysis over here. It's a snowball sampling because the data is not collected in the real time. In most of the people actually do snowball sampling in case of artificial intelligence and machine learning conclusion. Not all, but most. Now, data from non-random samples are not appropriate for analysis for inferential statistical method because there is no scientific basis for collection of the data. So there may be errors. Sampling error occurs when the sample is not representative of the population, and non-sampling errors like data may miss. You may miss some data. There may be analysis error, poorly conceived concepts may be there, under definitions may be there because it's totally a kind of arbitrary and non-scientific way of collecting data. That's the reason non-random sample data are very less used when you don't have any option. Now, let us come to the mathematics part of it, right? This was a very descriptive analysis. Let us come to see that how sampling distributions are collected, and then how do we reach central limit theorem from that. So proper analysis and interpretation of sample statistics require knowledge of its distribution. So unless we know the distribution, like if you have 100 samples, samples are collected from a small population. So how these samples are distributed, what's the pattern through which they are representing the data is very important to derive the conclusion. So sampling distribution is required, and this cycle is being presented over here. It will become much clearer when we show an example. So inferential statistics that I was talking about. So this big circle is basically the population. Sample is a small, population out of which we take, some data, and this way we want to, conclude some inference of the whole population. That is what is inferential statistics. That is what we are going to talk about. So inferential statistics is about estimation or hypothesis testing. Estimation is estimate the population mean weight using the sample mean weight. So for example, we want to know that what is the average weight of Indian population. Okay. So we will collect samples, and out of that sample, we will try to predict about the whole 125 crore people. Hypothesis testing is a very different kind of estimation. It's like sample evidence to test the claim that population mean weight is 120 pounds. So we have already concluded something, and that conclusion we want to verify out of the data, out of the samples collected. So that is hypothesis testing. So we already conclude, and we want to prove that this conclusion was true or false. And estimation is we want to predict something. So this is actually part of inferential statistics. Okay. Hope it's not too boring till this point of time. Yes. Or you have switched off your videos and audios and left.
No, sir. It's very interesting, and everyone is there. We just told the participant to even turn on their cameras. Just 5 minutes.
No problem.
Okay.
And with that's okay.
Okay. Sure, sir.
Between I just keep on pinching so that people do not sleep. Okay, sampling distribution is a distribution of all possible values of statistics for a given size sample selected from a problem. So we are not now coming to the core mathematics now. Now we have talked about what is a sample, how do we collect samples. Now we are trying to represent the distribution of the sample. Now distribution of the data you might have studied already, because this distribution in fact describes mean, median, mode, and variance, right? So if you recall, in the standard or the normal distribution, you see if there is a variance of rho, then the 38% of the population from mean to the 1 degree of variance, that is x plus rho and x minus rho, is covered, right? And 78% of the population is covered into x plus 2 rho, and 99 or 98% population is covered from x to 2 rho, right? So this particular aspect you might have already studied in the initial days of statistics, right? So similarly, here we want to analyze the distributions of the samples collected out of the various methods described, and more particularly, stratified sampling or the cluster sampling, because clustering is a very popular technique that we use. So types of sampling distribution. So sampling distribution is sampling distribution of the sample mean, okay, sampling distribution of the sample proportion, and the sampling distribution of the sample variance. So all these things are known to you. Mean, you know. So mean of the sample or the sample proportion, right? How much percentage you have actually drawn as a sample, and the variance. So these all are distributions depending upon the number of samples you collect. So these are types of sampling distributions, and all play a very important role in fact. So we'll talk about sampling distribution of sampling means. So sampling distribution of mean here is an example. Assume that there is a population of 4 people. Population size is 4. Just for example, actual data is large. Random variable x is the age of the individual. So we define a random variable x, which is describing the age of the individual. So values of x is 18, 20, 22, 24. For example, that's the actual data. Now here is the example where the mean is summation of the age of all 4 people divided by 4. So mean is 21. Okay. Variance is what? Deviation from this mean. So 21 minus 18 and divided by n. And when you square, why do you square? I'm not describing it, and then you take the under root of it. You might have studied in the very beginning days of statistics. There is a reason why do you square this variance, the mean minus variance, and then take the square root. You might have actually eliminated the square root also, but what problem that caused, you should go back and check. This comes out to be 2.236. Okay. Now uniform distribution is like 18, 20, 22, 24, and the probability of occurrence of 18 is 1/4. Probability of occurrence of 20 is, so all are equally likely. So therefore, this is uniform distribution. Okay, and here we have described that. Okay, so x is a random variable, and this is the probability of occurrence. Okay? So that is 0.25. That is 1/4. Okay. Now, developing a sampling distribution, and then what is a sampling distribution? Try to understand. Now, out of this 4 population, right? Population of 4, we want to pick 2 people. Okay. Now, when we want to pick 2 people, we want to know that what is the mean age of these 2 people. Okay. Now, there can be one combination that we pick a person of 18 years of age. Right, all people have an equally likely chance. So the first person chosen is of 18 years of age. Second person may again be of 18 years of age, 19, 20, 21, right? And that is, with replacements. That then only it is possible, right? So we are replacing people from the other as well. So these are the various permutations which are possible. And how many such permutations are? 4 cross 4. So 64 combinations are permutations are there. So 2019, 2020, 2021, 2022, 22, 20, 22, 21, 22, 22, 22, 23, and so on and so forth. There are 16, samples. And out of that, if you take the average of first sample, that is 18, so you get average of 18, right? Average of 19, you get for the probability of average of 19 is slightly more than 0.1. I will tell you why, because there are 16 such samples, and each sample or each combination permutation has an equally likely chance. So it is 1/16 in fact, right? So it's no longer uniform now. So you see, so here it was uniform because everyone was having a probability of 0.25. Here, everyone is not having a probability of having the same, probability, right? So they are having, so chances that the population is having an average of 18 is, it's different, 0.25, because 18 over here is just 1. So 1/16 is the chance. 19, 1, 2, so 2 by 16 is the chance that you get 19, 20, 21, 23, and so on, so forth. 21 is highly likely. So 1, 2, 3, 4, right? So 4 by 16. So 4 by 16 is 1 by 4, that is 0.25. So 21 is having 0.25 probability of having these numbers. And this way, the probability distribution of various numbers are very different. So this is not an uniform distribution you see in bar diagram. Okay. Now here we will try to calculate the mean and sample. So if we calculate the mean is summation of all the samples. So 18, 19, 21, 24. So these are the various samples that we are taking over here. 18, so mean we are taking for all the permutations. So summation of all 16, because they are 16 in number, divided by 16 comes out to be 21, which is same as the previous one. Okay. But the variance will vary. If you see, the variance is, there are 16 variances, and then it comes out to be 1.58, and earlier it was 2.236, remember, right? So this is, variance is lesser over here. Okay. So this is when you pick two people, to get the average age by replacement, right? So you replace one person by another. Okay. So comparing the population with the sampling distribution, that's the most important thing that we want to take. Example is not that important. So the average or mean is 21 over here, but the variance is 2.236 for a population size of 4. When we select, two people, so sample mean distribution of two, selections is 21 mean, and the variance is 1.58. And this is the distribution which is non-uniform. Here the distribution was uniform. Okay. Now similarly, we may have a very different kind of distribution. There may be exponential distribution. This is exponential distribution, which suggests that the likely chance of this particular data is very high, and then this is actually decreasing with respect to various data. And this is, the decrease is exponential. This is exponential decrease, distribution. So means of 60 samples from exponential distribution is a non-uniform distribution. So you see the difference. If you take the means, the sample is exponential distribution. But if you take the means, the distribution of the means of the samples, it becomes a non-uniform distribution, which is like this. So that is very important, and that is what we want to actually characterize and study over here, which is a very powerful statistical technique used in machine learning and deep learning as well. So means of 60 samples we have seen over here. Again, it's a non-uniform. So expected value of the sample mean is x bar, that is summation of all the means available divided by n. That's very simple. We have already done this example. So x bar we can calculate. Variance is rho square by n, plus we want to actually skew all the corrections that we want to make in this account. So if the sample size is n, is not a small fraction of the population, it's large, then the individual sample members are not distributed independently, and then therefore we divide n minus n, and we take the ratio of n minus 1 and n minus 1. So this difference is actually skewed over here, and that variance is recorded. And with that variance, we calculate rho x, and rho x is rho x is square root of this. So this square root of rho becomes rho under root n, and then we take under root of this. So variance and then rho, mean and variance is calculated like this. Okay. Okay. If the population is normal what? It's a normal distribution, right? Normal distribution is like a bell-shaped curve, right? You have already studied, so I'm not talking about the bell-shaped curve over here. That requires another, 1 hour or half an hour. So mean is calculated like this, okay? And if sample is not large relative to the population, so if you are taking small samples, then you must remember this formula. You have to skew the smaller size of the samples to actually have a more accurate prediction. So if the sample size is very large and normal in distribution, then this, otherwise you take this formula. Okay. So what is dead value? Z value is actually a uniform scale of, you know, bringing the means together. So when you have a different mean out of this, sample size may be varying, sample properties may be varying, and we want to compare all these things together, then Z value is very important because we want to bring all those on a simple scale. So Z value for a sampling distribution of, X bar is X bar minus mu and divided by, so X is the sample means of all the sample. Mu is the population mean, okay? Population mean and sample mean. You understand the difference? Okay. Sample is mean means, or there are samples taken and we want to take the mean of those samples. So suppose there are k samples, so k, k divided by, all the means, the summation of all the means divided by k. Population mean is different. Population means is entire population divided by n. And rho x is the standard error of the mean, right? So we calculate the Z value out of that to bring them all onto a uniform scale. So Z value for the sampling distribution of the mean is this. Now, how does it depict? So these formulas you can get anywhere. So I'm not worried about that. But conceptually, you must understand what is the mean. So normal distribution of a population is this, which is a bell-shaped curve. Okay. Now, normal sampling distribution may be a skewed curve. So, you just press this curve, from the both sides. So you get a larger mean, but, the shape of the curve remains same and it becomes, it is normal. So so X bar is unbiased. So you see that the characteristic of the curve remains same and therefore mu X is equal to mu. So this is the sampling distribution property. But otherwise, also it may be true if this curve is skewed in either direction, so either left direction or right direction, and then when you take the mean of the samples, then you get a normal distribution. So this we will see in a short while. Okay. If the population is not normal, so from here we are coming to a central limit term. So this is normal. So this is a normal distribution. So there is no difference as far as mu x is concerned because X bar is unbiased because the properties do not change. But if properties change, then we have to talk about central limit theorem. We can apply central limit theorem even if the population is not normal. Sample means from the population will be approximately normal as long as the sample size is large enough. That's the only condition. So properties of the sample distribution is mu x is equal to mu and rho x is equal to rho by under root n. We will see that example. Now you see this sample. This is the population distribution. So population distribution is skewed on the left hand side, right? The mean is skewed. So, but we take the distribution of the means, it becomes normal distribution. So that is central limit. So central limit theorem says that instead of analyzing the data on the population, if we analyze the data on the mean of the samples, then it becomes normal distribution. And we all know what is the advantage of normal distribution. Analysis becomes easy. So you see, population distribution is right skewed, and when we take the sample distribution, it becomes normal, provided n is very large, population is very large. So you see this data, this is a smaller sample size, but when we take a greater sample size, it becomes normal. You see, right? Okay. So central tendency, variation, these are formulas that is. So how large is enough? Large should be 25. From where this 25 comes out, I'm not going into the details. That is from a lot of statistical analysis. So if you want to analyze the marks of a student in class, remember for grading systems, for any kind of analysis, minimum population size should be 25 if your data is not normal distribution. If it is normally distributed, even 4 data will work fine. But normally the marks are not normal, normal distribution, which is a reflective of the fact that your question paper is either very tough, question paper is either very simple, it's not normal distribution, or otherwise the class has not been taken properly. So if any reason may be there, which actually describes that the distribution of the marks of the class for a test or a end semester examination is not following the normal distribution or a bell-shaped curve. So in that case, central limit theorem may be applied, provided the population size is large enough. 25 is the minimum number, greater than 25 works perfectly fine. So this is, take an example. Suppose a large population has a mean of age. Okay, you get standard deviation is 3. Suppose a random sample size of 36 is selected. So what is the probability that simple mean is between 7.8 and 8.2? Okay, so we can calculate that. So it is greater than 25, so it will work. Central limit theorem can be applied. Sampling distribution x is approximately normal. Mu x is 8, which is already given. Standard deviation is 3 by under root 36, because 36 is the sample size. So rho x comes out to be 0.5, and now we simply apply the formula. And the formula is, we want to know that what is the probability that the mean lies between 7.8 and 8.2. So the probability is 7.8 minus what is the mean, right? So this divided by rho x, so that is 3 into 36, under root of 36, and then mu x minus mu divided by rho by under root 36, and we get this value as 0.3. Probability that the mean will lie between 7.8 and 8.2 is 38%. Okay, so you see, this was the sample, which was not normal distribution. Anything can be there. That's why I've written question mark. And when we do the sampling distribution, so we have taken the samples, and sampling distribution comes out to be a bell-shaped curve or in a normal distribution. We want to know that what is the probability that the mean lies between 7.8 and 8.2. So we want to calculate the area of this. In Python programming, you can calculate the area, the blue area, by just giving a simple, data, and there is a standard tool for that, and that will come out to be, the probability will come out to be 38%. Okay, so this is how we standardize the thing, right? So if you have any questions, you can ask. This is all from my side. What about 1 hour lecture? I wanted to cover, the much more, things related to central tendency. And central tendency is a large topic, so it can't be covered, like this in online FDP, because statistical studies require classroom interaction. So you need a lot of examples, and onboard studies. So online, FDPs have their own limits. So this is the thing from my side. I am new to data analytics, but nonetheless, I am, I am pushing forward myself with this, which relates a lot to formal modeling and all those things. Rather than picking up machine learning and data analytics, I am machine learning and AI. So I am actually focusing more on data analytics, for which I see a great future because of the mathematical skills required over here. In times to come, you will find a very less expert people who are into data analytics. In AI and ML, you will find large population. Why? Because they just have to actually identify some sort of feature, and those features are applied onto the standard tools to get the result, which is an easy thing. I will not say it's not useful, but it's an easy thing. But data analytics requires a lot of presumption, a lot of analysis and mathematics on the top of it to conclude a outcome. So you must actually promote students to take up data analytics as a career as far as the future in computer science or IT. If you have any questions, I will be happy to answer as far as what I covered today.
Participants, any queries or questions? You can even unmute yourself, or you can type the question in the chat box also.
I'll through the slide so that you can recall what is what.
So many participants have already started typing in chat box that the concept was very well explained, and thank you so much for a nice presentation. And thank you so much, sir, for motivating us to take up as data analytics with much more importance. We have one query, sir. One of the participants has asked this question: which type of sampling is more appropriate for research?
So it depends on the research program. Actually, somebody can describe, what kind of sampling is appropriate for uniformly for all applications. So it depends upon application to application. And say, for example, elections are coming, and if you want to make, predictions about the elections, the first thing you need a data. Based upon the variance in the data, you have to, and what kind of prediction you want to make. Based upon that, you can go for cluster sampling, and so on and so forth. But on the same time, if you are doing audit of purchase orders or bills and so on and so forth, you can go for a stratified sampling, or where you can actually randomly pick number. Like IT returns are verified by income tax department in a stratified sampling method. It's not a clustered sampling. So or sometime when there is a large data, they form clusters and then go for a stratified sampling. So in practical application, there is a mix of many sampling methods, but nonetheless, it depends upon one application to another application, where and what you want to conclude. So it's very difficult to answer that this method is applicable uniformly for research problems.
Okay, sir. One more question is there. Does more variance in a feature imply a better feature, or is it the opposite?
Opposite. So more variance will mean that data is not uniformly distributed, right? So if it is bell-shaped curve, then it means that I said, there is a thumb rule that from the mean on either side of the curve, the single variance will cover 38% of the population. Okay, and if you travel twice the variance from the mean, it should cover 78% of the population. If you travel thrice the mean size from the mean, then it should cover 98 to 98% of the population. But if the population is not uniform distributed, it will not be followed. Nonetheless, there is a Chervos theorem. It suggests that even a slight variation, that is 1 minus 1 by k square. So k is the value. So whether you are traveling one the mean size, then it is k is 1. If you are traveling twice the mean size, it is 2. So 1 minus 1 by 2 square is 25%. So I said 38%. They say that 25% is also acceptable. If you travel twice the size, then it becomes 1 minus 1 by 4. So that is 3 by 4, 75%. I said 78%. If you travel 1 by 3, so it becomes 1 minus 1 by 9. That is 8 by 9. So 8 by 9 is about 90%. I said 98 to 99%. So Chervos said that this is also acceptable, right? But beyond that, we don't, accept the distribution, and that's why we do sampling. So even if you have capability to actually, collect the data from all the entire population, then also sampling helps, because the means of the samples actually are uniformly distributed, and then this uniform distribution can be used to infer the data. That is what I explained in central limit theorem. Okay, so less the variance, better the data, and better the prediction. Variance means what is the size of the population which varies from the median. So for example, if I've collected the marks of the class and the median of the class has got, let us say 20 marks out of 30, then how much population varies from this 20, right? So suppose variance is 5. So how many people are between 20 to 25 and 20 to 50? So if they are more than 50%, 70%, and what? So this actually is a reflective of the fact that the class was taught well, right? Because most of the population is covered, between 15 to 25. Of course, some people will be 28, 29 also, but they are rare. And the question paper was appropriately framed. That is also a reflection, because if you prepare a very hard question, then large population will guess less number. If you prepare a very simple question, large population will get a very high mark. Both are bad reflection of the entire, process that has been conducted. That is what is the, beauty of the statistical analysis. So the percentile that you calculate, for example, in GATE exam, they say that, somebody has scored, 75 percentile, 99 percentile. What is percentile? Percentile is just so it is a variance from the mean. So suppose the highest marks have been obtained by a person, and we say that one has got 100% or 100 percentile, then there is a population 5% which is actually lesser than or between 95 to 100. So if you have got 95 percentile, then it means that 5% population is above you, right? If you have got 90 percentile, it means 10% population of the entire sample space is above you. Now, if you talk about computer science, in computer science, lot of people appear for GATE exam, which is largest in number, right? So 10% will mean not many people, right? But if you talk about, let us say, textile engineering, in textile engineering in the entire country, 1,000 people appear. So 10% variance there will mean hardly 20 people are above you, right? So it depends upon the sample size, that how many people are above you or below you. That is what is percentile, and that's why the percentile in computer science branch or these are very high. Reason being, the population size is very large. So this is basically deviation from the highest value. Similarly, when you calculate the deviation from the mean value, this becomes the normal standard deviation in case of bell curves and normal distribution. Okay. So that is primitive statistics. You should go back and learn very carefully and see that how this percentile is being calculated, and then the concept of variance and mean will become very crystal clear to you. And try to calculate the percentile. You may ask question, I have never heard that a person in GATE exam has got 100 percentile. People get 99.99 percentile, but not 100 percentile. This comes out with the fact because many people actually apply for the exam but don't appear into the exam. And when this happens, the sample size remains the same. Sample size is not about how many people appeared into the exam, but how many people applied into the exam. And those people are the people who have actually scored 0 marks by non-appearing. So you should go back and do some examples and try to see that how percentiles are calculated, and try to calculate percentile in your class marks, and try to calculate grades in your class marks, which will actually give you in hand experience of doing statistical analysis. And you don't have to write a very large program. Just use Python library, use NumPy and Panda, and you will be able to do lot of analysis and get the answer. Just do as an experiment basis. Nothing to do with grades and all, but just do as an experiment basis, and you will see how beautiful these distributions will represent. Make sometimes tough questions, easy questions, see how the marks are varying, right? And that will reflect a lot of things. Word is very large, can't be covered in 1 hour.
No, sir, you have already explained with such fine examples also. Participants, any other query? I think it's clear with them, sir. Thank you so much for this informative session.
Thank you. The opportunity. Not too fully, but the word of mathematics and statistics often
Oh,
drive
thank you, sir.
in its context.
Yeah. Our team will get in touch with you for these slides, because all the participants, they are already requesting for them.
Okay, so I will send it. No problem.
Okay. Thank you, sir.
I leave.
Yes, sir. Yes, sir. You can leave the meeting. Participants, we'll be starting the next session as soon as our next speaker would be here. Participants, we are facing some issue. As soon as our speaker joins, we'll start the session. Good afternoon, sir.
Good afternoon.
Good afternoon, everyone. I welcome you all to the next session. We have with us eminent speaker, Professor S. Sundar. Professor S. Sundar is currently a professor in Department of Mathematics, Indian Institute of Technology, Madras. He also held the position as head of department from 2017 to 2020. He has done his PhD in mathematics from IIT Madras. He also has associated with German Academic Exchange Service. He has been Fellow of the Indian Academy of Mathematical Modeling and Simulation, IIT Kanpur in 2018. Along with that, he has been Chairman, HSEE and Vice Chairman, JEE Advanced, IIT Madras in 2014. JEE Advanced, IIT Madras in 2015. He has published numerous research papers in national and international journals of repute. He has been a member of SERB DST Program Advisory Committee, Mathematical Science. His research area includes numerics for PDEs, mathematical modeling, and numerical simulation. Now, I would like to request Sir to start his session.
So, good afternoon, and there was a delay due to the Zoom link, some technical hitches. Thanks for this wait, and I tried it since 11:40, but it was not connecting from my side. So, extremely sorry for the delay, and I welcome you all for this FTP, and I congratulate and I appreciate this college for taking such initiative to hold this FDP faculty development program, this webinar on machine learning. So what I'm going to talk today is about the mathematics of machine learning. So as you all know that machine learning, artificial intelligence, these are all, these two are very catchy keywords and very attractive words. And among the students, faculty, and across the subjects, okay. Even I teach that means my students, MTech students, or MSc students, or some BTech students here. Everyone wanted to do project on machine learning. Everywhere they talk about we need machine learning projects, machine learning, or artificial intelligence, machine learning. This is the thing which we want to get expertise, because a lot of from outside the job market for this machine learning techniques, machine learning algorithms, and the job market is really, the industrial job market is very flourishing on this. So that is one. That is why everywhere everyone comes out with the machine learning, and even some students who are contacting me from outside, they talk about, sir, it's a machine learning. I would like to have a project on machine learning. It's good, but what is the background they have? That's very important for me. Whenever someone coming like this, I have to be very. So most of us are faculty. So we have to be very careful that what level of understanding that machine learning these two, irrespective of the of the course what they do. It's not machine learning or artificial intelligence is not a word from computer science. It is basically each and every department. Go to mechanical, go to metallurgy, go to mathematics, go to physics, go to any bio. Everywhere they use this. They wanted to do, the students from that area wanted to do something on machine. So it's not the area only to computer science. It's now it's a wide this one, and that is why the importance. It's very true. And also some colleges or some universities, they started introducing a new course, a master's in machine learning, a master's in data science, a master's in machine learning and artificial intelligence. So there's a lot of them, and many this one depending upon the need, because naturally we prepare the students so that they are equipped with the latest developments, and they are developing that skill, and they are what is that, the industry, according to the industry need outside, they are trained, they are well trained. So the machine learning is now is a catchy word, and from the students' point of view, from the project's point of view, from the university point of view, they wanted to start a course, a master course, a master's in machine learning or artificial intelligence. Even from the courses point of view, meaning if they want to introduce a new course, many places they already started the course on mathematics of machine learning or machine learning algorithm or generally machine learning. So question is, have we understood what is machine? That is a fundamental thing which we have to. So in this 1 hour talk, we have to really understand what you are. Then we have to really in this particular in 1 hour talk, I am trying to take you. I cannot cover the entire thing because machine learning it's a big topic, and it's like another. It's like a heavy course. But what are all the important things which we have to as a teacher? If I want to teach machine learning to my students, and what is the thing, and even as a faculty of IIT and dealing with, if I'm taking some projects related to machine learning, I have to, how do I do that? Okay. So this is why the topic becomes important, very challenging, and it's very important. So, but important, the main thing is this message what I'm trying to give you is the mathematics of machine learning. How strong mathematics, more mathematics we know, the deep mathematics we know, more mathematical thinking we have, better our machine learning. So that is the main thing. So without mathematics, so the strong base is mathematics. So the base for the machine learning is, that is why the topic today, what I am going to discuss is the mathematics of machine learning. Without that mathematics, without that, even if I teach as a course to my students as a machine learning course, it's very important that these mathematics, these topics of mathematics are very, very important to the students. Or even if I want to handle the projects, if I want to develop a machine learning algorithm on a given real problem, then all these things comes into picture. So mathematics of machine learning is a must, and mathematics is a strong base for machine learning and artificial intelligence. So this is the message, okay, and that is why this topic. And I'll give you an overview so that more details, if some of you are interested, you can write to me. So I am ready to discuss, ready to collaborate, ready to work on certain problems. We have a lot of ideas, So then we try to work on how to develop the machine learning. Okay, so it's a kind of bird's eye view, a quick view within this 1 hour 15 minutes talk. So today, if you take a modeling, today it's a very important everywhere. So the modeling is mathematical modeling play a crucial because of your affordable computing environment, because of your high-end computing environment, which is available in terms of your desktop, laptop, and your mobile. So this modeling, mathematical modeling, becomes more and more important across the industries. You let it be a food industry, let it be a finance industry, let it be a pharmaceutical industry, let it be a material industry, let it be an automobile industry. Anywhere you take, everyone wants to have some kind of software, some kind of automated systems. They wanted to implement, and they tried to. So they wanted to use heavily, or they wanted to bring it as a processor or as a apps. Okay. So then, in order to, before they go to the actual thing, they wanted to do the virtual. Virtually, they wanted to understand what is happening. So the real world, one is the real world, another is the virtual world. The real world is what we are saying, every problem, every sector. Okay, the real world, one thing, and the virtual world is the mathematical mapping of that real world. And in terms of your computing and in terms of your visualization, which you are showing it, or in your analysis, what you are showing it in your. So this is the virtual world, and it's a mapping, mathematical mapping, which gives you the virtual world. And we try to see what is happening in the reality. We are going to simulate in the virtual. What is the why we need? We can predict. We can understand. We can predict. Okay, and whatever modifications, whatever input you want to adjust it, you do it in virtual world instead of real world, and try to see what is the kind of result you get it. And you can predict what is going to happen for the input. Based on the prediction, you can have a decision making. Okay, you can have a decision making. So that's it. You take a finance market, take a stock market. Everyone, they wanted to have some kind of prediction. What is going to happen? What is going to happen? What is going to, if I'm investing in this stock, if I'm investing in this stock, what is going to happen? So they, based on that prediction, they try to invest and then take a decision. Any industry. And the best example is your automobile industry. Today, all your cars, what is running on road is totally automated. Okay, completely automated. You just sit and tell, even through your words, automatically it understands. And so your car is not this one. Your entire car today inside is so much of technology. So much of technology, airbag to whatnot. So much of technology. So more than the mechanical, the technology, it's driven, and the entire internet, everything is inside that it is controlled. You speak, automatically it understands, and it understands how to move around. So so we are in the modeling, mathematical modeling becomes more and more important. And in order to make the system, entire system, irrespective of the problem, make the system, automized system. Okay. So this is why the moment you say mathematical modeling, today, the meaning of mathematical modeling, it's another this one is basically we need to do it through machine learning. Okay. So today is the world of data. And your models are completely data driven. The moment your mathematical models are completely data driven, because the data is available to you. You don't need to assume anything. Your data is, everything is available to you. Any sector, any sector, you go to any sector. I don't want to mean one by one under this one. Any sector, you go to you go to what is that? The medical. You go to pharmaceutical. You go to food industry. You go to material industry. You go to agro industry, agricultural industry. So everywhere the kind of the data things are available to you, because through some forms, it might be as a text, or it might be as a video, or it might be as an image. Everything is available. So it's a data driven model. So you need to suppose, for example, if one wants to construct a best bridge in the world, and this one, and they need not have to worry about what is that, assume a certain this one. Some of the best bridges in the world, and how the information or how those data on those best bridges in the world is available to you. Okay, and in order to design a new bridge based on that setup with that real data, whatever this one, in order to design, you have a new design based on those some of the best bridges in this one. You can this information is available to you. You don't need to assume certain thing. You don't need to. So basically, your world is data driven too, and it is going to be like that. And even in different forms, even in this one, and we want everything to be in a faster way. Because please understand, it's not only that this one, whatever we see it in reality, we wanted to see it in virtual. Whatever the reality, in order to, we wanted to predict what is going to happen in reality, we wanted to see what is the kind of predictions through the virtual. And all your virtual models, which is a mathematical model, are totally data driven. Okay. So the moment you say the data driven model, the machine learning is the base. That's it. Machine learning is a base. So that is why today the machine learning becoming more and more important, and many. So what I am saying is, the modeling 20 years before, 30 years before, or I would say that 30 years before, the modeling, mathematical modeling, the way in which we look at the model, we look at the problem and try to model, the way in which we look at 30 years is now different totally. Because your information about the entire thing is a data driven. So the moment you say data driven model, the machine learning is important. The moment you say machine learning, then you must have a strong base in mathematics. And that is a fundamental thing. Without that, you cannot do that. You cannot evade, because we are all teachers. And I am a teacher, some of you are the teachers, some of us are students. And when you want to make a student to develop a machine learning, understand what is machine learning, when they go out and joining in a particular industry, they are expecting the student to do that. Then they should understand it's not the user, end user. He is a developer. Okay, he's a developer. So in that case, he has to understand the intricacies of mathematical modeling. The intricacies of important thing, what is a data-driven model? Okay, so what I am saying is, so today mathematical modeling is very important, and in fact after why all these things happening? You just imagine, it's because of your affordable computing environment. 1 minute. Hello. Because of your affordable computing environment. Because of your everything is automated, and everything you can do it in real time. You can do it at a real time. The predictions, then the decisions, then so All industries. I don't want to mention one by one after. Any industry you touch today, it is that. Okay. So the data-driven models are important. So machine learning, the base of machine learning is mathematics. The moment you say data-driven model, then machine learning is interpretable, because we need to interpret the interpretable models. Interpretable model. Okay, so data-driven model. The next point which I wanted to, because you have to understand what industry is doing, what that industries are asking. Okay, from the today we are connecting to so many industries. IIT Madras as IITM Research Park here. A lot of industries are their research division is sitting here. Okay. What is that industry is asking? What is that industrial problem? What do you mean by industrial problem? What is your modeling? The moment you go to the industrial problem, this one, the industrial problems are basically mathematically, when you call it, these are real problems. I would say that the real world problems or the industrial problems, or fundamentally the inverse problem. Mathematical term is called inverse problem. Mathematically, it's called inverse problem. So what is the inverse problem? Because whether we know it or not, unless you understand this idea of inverse, this is the inverse problem. The meaning why I am telling is, you see, you want to develop a mathematical model and the data-driven model. You want to develop a machine learning algorithm through your model. In order to, the machine learning algorithm automatically understands the situation. Automatically, it gives you some kind of prediction, and based on that, you take a decision. The industry, what the industry is asking, all the real world problem is they wanted to the industry wanted to have a desired output. Industry now do not want, if you have a model, if you have an algorithm, if you are producing a result, does not mean that the result, whatever you are producing it, yes, fine, you are captured the actual problem and you have produced the results, it's fine. But we wanted to have this result. For example, if I go to the automobile industry, there is a concept of shape optimization. You have to optimize the shapes. Okay, up to automobile industry, the concept of, or even in the cycle industry, all these things you go, the sprocket shape optimization. The shape optimization is a very important problem. So industry is asking, yes, we will give you we will develop a model, mathematical model through your existing data, and we will tell you that which is the optimal shape. But the industry is asking, I wanted to have such a shape. Yes, you give me the optimal shape. Among that, you give me that such a shape. The industry is asking you to do this. Can you improve this? Can you make it this one? So what I want to, like every industry, they wanted to have, you are as a specialist in modeling, as a specialist in machine learning, you are now looking at the real problem, as a data driven, and you are collecting the data, and the data through which you are trying to model, model, okay, and you are developing a machine learning, assuming the machine learning algorithm, okay, and through which you are trying to take the information, that input the data into your model, then it is going to give you the kind of outputs. And the industry is asking, yes, but I want the desired one. So this is called inverse problem. If it is an inverse desired one, what is happening is, if you want to have a desired one, then what should be the input I should adjust in such a way that I get that desired one? Most of your control problems, if you go to any electrical or electronic, these are control problems. You have some kind of controls, you can do that. Based on that, you get a desired output. So this problem, so you must understand why this important, all these things I'm preamble I'm giving you is because of without understanding, because the moment you touch machine learning, please, you are in the, you are doing the modeling and you are developing data-driven model. So all 100% your real problems which you want to try to model and do this one way, except whatever problem you take, please understand, this is the industry is asking the desired output. How do you do that? What should I adjust it in your input in such a way that I get the desired output? Or what kind of controls I have so that I get a desired output? So this inverse problem is a mathematical key. But how do you do it in your in this type of models? Okay, so please understand. So you have to be. So what industry is asking, how do you adjust it in such a way that you get that model? So the problem becomes more challenging, the model becomes more challenging, and that too data-driven model using machine learning becomes more challenging. Okay, so what I am saying is understand that industrial. Whenever they take a project and you are a member of that particular team, and your client will ask you, what is the, okay? So you are in the world of mathematical modeling, the data-driven models, and we are in a position to develop a machine learning, techniques, machine learning algorithms, in which in turn that will help that particular industry or particular problem domain, that means a particular industry, to have predict what is going to happen, and based on that they can take a decision. So with this, the machine learning, the base, without the math, that's what when I tell the inverse problem and all the things, I'm trying to tell you, basically, when you are, even if it is a data-driven model, please understand you are going to collect the data, you are going to have the data, okay? And based on the data, you are going to develop a model, okay? Machine learning algorithm. So your mathematical fundamentals must be thoroughly strong. So that is why, as a teacher, it's our responsibility to see that our students are taught a thorough mathematics. They cannot evade mathematics. As you are evading, definitely they cannot contribute. And they should know how to convert that one into a coding. It's not that you are doing it as on paper and pen. It has to be computed. Everything should be on the system. Everything should be computed. So if they do not have how to convert that algorithm or that particular thing into a program, into an effective program, and knowing the computing environment, what is the current computing environment, which platform you are basically, then they need to have a so it's not that just a data-driven model and you are developing the algorithm and leave it like that. It has to be computed. It has to be, then entire thing comes as a processor or as some kind of software or some kind of app. Okay. So what I am saying is model, data, okay, and the computing is a very important. Without computing, don't forget it. Forget about this. All these things must be taught from the beginning, even from the first year of your BTech or this thing. It has to be taught thoroughly. Unless whatever you see it, whatever you do, the mathematics, you should have a mechanism of converting that one into a coding. Okay. So with this, now let me get into the overview on mathematics of machine learning. Okay. I'll share my slide so that are you able to see the slide? Please, any one of you, please.
Yes, sir. Your slides are visible.
Yeah. Okay. Now let us journey. So what I have so far I have emphasized on this one is today when the moment you say mathematical modeling today is basically a data-driven models. The moment I say it's a data-driven models, the machine learning is a very, very important tool. And without mathematics, strong mathematical background, you cannot even touch because we are in a position or position. That means the person who is on this particular thing, we are not the end user. Please understand, we are the developers. And trying to model the real problem into a mathematical mapping and the data-driven models. So it's going to dominate. It is going to be strengthened further and further and further. And the computing world one side, mathematics is another side, and combining that machine learning things another side. So this is a very, very, very important field today. And the industry takes this information, even let it be a manufacturing industry, let it be agro industry, let it be any industry. They try to look at the model, they try to see, visualize it from on your screen, okay, through your this one. Based on that, even it's a textile industry, okay. So they try to see everything on that. Then they go to the production. They go to online because they don't need to do trial and error. All these things, whatever they wanted to do it, they can see it, and they make, based on that they can take the decision how they are going to do it in the reality on the real field. Okay, mathematics of machine learning. Let us go into that part. So these are the overview. I will come to that part later. See, for example, machine learning, please take it in mind. Linear algebra, one has to be strong. Definitely, you need to have a vector calculus, idea of vector calculus. You cannot run away. Probability and distributions. These are all mathematical tools, please understand. Probability and distribution. These are all mathematical tools. Optimization. You cannot touch linear algebra and get away. You cannot touch a vector calculus and get away. So probability and distributions, optimization. These are all the mathematical tools one need to understand. One problem, if I take one problem, I use some concept of linear algebra, I use vector calculus, I use probability and distribution, and I use optimization. And if we are the modeler, when we are trying to develop a model and you don't know what is the optimization problem, how do we think of it? So this is one side, mathematical tool. From the machine learning side, what is the base? This is from the machine. If I talk about machine learning, okay, and from the machine learning side, I will be basically, I need data and models. I will be linear regression. So these two are very, very important in your dimensionality reduction. Then I have what is it? What do you call the dimensionality reduction and clustering and classifying. So these are all basically that I will come to this part later. Slick is different, which is one type of supervised learning example. If time permits, I will come to this part. But what I am saying is the 5 and 6 is corresponding to the machine learning. But in order to do all these things, what is the mathematical base tool through which all these things are built up? Is linear algebra, vector calculus, probability and distributions, or optimization. We need to understand what is probability. We need to understand what are distributions. We need to understand the vector calculus or calculus of higher dimension. And all these things, another important thing, the linear algebra. So these four are mathematical base or mathematical background. And on the machine learning, you have data and models where I have linear regression, I have time series, I have dimensionality reduction, I have clustering and classification. So these are all the. So one side from the machine learning point of view, okay. And in order to do all these things, I will be using this concepts of linear algebra, vector calculus, probability distribution, all these things must be taught thoroughly. Must be taught thoroughly to our students. As I am thinking that I am a faculty I am addressing my students in order to make sure that the students has to be those who are interested to do this one, and this has to be taught very clearly and very thoroughly up to that level. It's a bachelor level or master's. So, okay. What is machine learning? Machine learning is regarding designing algorithms. That's what I told you, machine learning algorithm that automatically brings out valuable information from the given data. That's what I told you, data-driven models. The data is available to you. The real data, what you are seeing it in the thing, is available to you in different forms. Let it be a video, let it be a image, let it be a voice, let it be a some kind of audio, all text, everything is available to you. And a powerful computing environment, affordable computing environment. Okay. So machine learning is regarding designing algorithms that automatically, this is very, very important. Please keep it in mind. That automatically, this is important, automatically brings out valuable information from the given data. And that is the one which we try to model. And that is the modeling, valuable information. How it gets the valuable pattern from that. Okay. So there are three core concepts of machine learning. One is data. Second is a model. Third is a learning. That's called it's machine learning. Third is a learning. So you take the data, you try to model according to your, okay. So next is the model. And through which you learn it. So you allow that from the history, from the available data, or from the data through some sources, you are taking the data and you are to develop the model, and this one you make your system to learn. So first phase is the learning. So in the machine learning, the main important thing is through the history. You have history means you have the data already available. So from the history. What I mean by that? If you go to to a hospital, the doctor is a specialist in a particular disease. Suppose this one. The doctor is seeing the patients and he is asking the patient to fill the forms, and every time he is different patients of different ages or different zones and every. So that information about that patient, about that particular disease and how the things are going and everything is available on the system, available to him. Now the data is available. Now based on that data, we need to develop a model. We need to develop a hidden this one, allowing the system to learn about that particular problem domain. About that particular problem. They just collect the data. The data will be available in the form of a table, and every line of the table is a record. It's basically we call it as an example or a record. Every column of according to the particular problem, you have a column, and the column according to the column is basically these are all attributes. So these are all attributes, and basically what we are trying to do is from this one, is it not possible to identify such a pattern into and the doctors are entering the information according to certain, they have some, kind of note or kind of doctor's remark. Based on that, we try to understand from the history, we try to, that's a model, data and a model and the learning. What is the main thing? Once you develop a model, once the model is stabilized, whatever your model, the machine learning model or algorithm is stabilized, which is robust, or this one. This has to be applied on a unseen data. From the history, you learn it and use that one for a unseen data. Because whatever is existing one, I have the information. But the existing one, it's keep on learning, because as the time changes, your data is also keep on changing. Some more information is added up in your attribute, some more according to the problem, according to over the period of time, the data is undergoing a lot of changes. The machine is also undergoing, it's trying to learn from the existing data, trying to adjust it. Then it is applied on a unseen data in order to have the prediction. Because if the doctors are available, they will say that, okay, now the new patient is coming. They just enter the information and try to see from the data, whatever they developed this one, it is trying to guide you. They just give you a first-hand information about from the data, whatever that person is entering, whether what type of this one the doctor is able to identify. It is giving you some kind of prediction. Based on that, what is the advantage? Immediately the doctor will go for correct test, or without wasting much of time, you will get into the right test and the right treatment. Go to your financial market. Data is available. Data everywhere, the data is. So now we want to do the prediction according to the. So then use it on an unseen data. If you knew this one is in unseen data, so then that prediction is used. So the meaning of machine learning is designing algorithms, machine learning algorithms that automatically bring out valuable information from the given data. What is a valuable hidden knowledge? That is the one which we have here, that is the purpose. Then you see it on how robust it is. Then based on that, you apply it on a domain where unseen data, unseen domain, then you try to so 3 concepts in machine learning: data, model, and learning. Okay. So with this, now let us go slightly this one. So importance of mathematics in machine learning. While machine learning has seen many success stories, and it is going to be dominant. And there are softwares available to design and train rich and flexible machine learning systems. There are softwares available to design and train rich and flexible machine learning systems. So the mathematical foundation of machine learning are important in order to understand the fundamental principle upon which more complicated machine learning systems are built. So that's what the mathematical foundations are very important. So that's what I told you. What is the mathematical foundation of machine learning? The mathematical foundation of machine learning is basically the topics, whatever I'm going to linear algebra, the probability and distributions, vector calculus, optimization, the foundation. So that's all. So there are software available to design, train rich and flexible machine learning systems. Flexible, okay. Training them and applying it on a unseen data. Please understand. From the seen one, the unseen data, and the seen one is also dynamic. Please understand. So over the period of time, the data, the things are getting changed, and machine is also understanding automatically that what are all the things. When you are applying to on an unseen data, automatically it works. We are this one, the predictions are becoming more accurate with less error. So that's what. So it's very important that are important in order to understand the fundamental principles of all. So how machine learning works? So it's a decision process, and the error function is very important. How it's not everything is 100% or 200% correct. What is that error? Okay, we need to understand how much, because we need to say how much error we have to give. How far is it? 90% confidence, or 95% confidence, or 98% confidence? So depending upon that, or 99% confidence, are you going to, so there's a decision process and the error function. So all these things has to be calculated. Please understand, without that without that error, without that thing, we cannot just like that take the data and do something. It has to be brought it under the mathematical world. All your data, whatever you are seeing it, place it as a table, and each line you call it as an example or record. Each column you call it as attribute. What I wanted to try to understand, we need to develop an algorithm to learn from that data. What is the depending upon the need, what is the actual, what you want, what is the industry is asking for, but do it from the data. So how far it's a error, how much we can give the error. So without that, everything you bring it under the mathematical one. To look at it as an entire thing as a mathematical problem and a model optimization problem, because all the model, it has to be model optimization. So model has to be optimized. So the machine learning algorithms automatically works on a decision process. In turn, it gives you what is the error. So it is computing the error, because these are all happening. It has to be measured, please. But the moment you say computation, please understand, it has to be measured. Everything has to be that's a number. You have to be measured. Okay. So whenever I say that shape optimization problem, or if I take for example, the shape optimization problem which I am talking about. How do you know that it's optimal shape and it is able to take care of, because it's not only the shape, it is also the kind of component where you are, for example, if I take a sprocket, the cycle sprocket, the important of this, I am going to apply the force. I am going to apply this one. So the material, what is it? The strength of that particular component must be kept. So whenever I do this optimized shape, meaning instead of the original shape which you have, you are using it for the existing shape, I am going to modify the shape, meaning in order to bring out the less weight. Okay, so I need to remove the material somewhere. So it tells me where to remove the material. Then I am having a new shape. Now this says that this is the new shape which you can use it. Now you go to the production and you produce it. But how do I know that? It withstands that particular force when I'm cycling? Okay, they should withstand, because less weight advantage. Even the cars, why they want to go to optimal shape? The cars or total weight of the car will be less, marginally or considerably less. Meaning your fuel consumption will be less. Car will have a sleek. Every component of the car is optimal shapes. Your cycles today, optimal shapes. The furniture, what you are doing today, is optimal shape. It will not have more weight, but it will give you such a strength. But when you can lift it just like that. But what I am saying is the strength of the material. Now, how do you know that it is maintaining? So there must be a decision process. There must be error function. How do you know that? Because you are getting it from that algorithm. So how do you know that? You must know the error function. Then we need to have a model optimization. The model has to be computed or evaluated, optimized model. So what I am saying is machine learning works in this way. So please, you have to keep that in mind. So it's a decision process. The moment you must have an error function, you must have a model optimization process. Okay. So useful mathematical tools, that's what I told you. One is linear algebra, vector calculus, probability and distributions. That is a fundamental in which it is a optimization. This we cannot ignore. That's what I'm. Okay. So it's not a lecture on linear algebra. It's not a lecture on vector calculus. This is not a lecture on probability distribution, because that's why you know it. Without going through all these things, you cannot teach any course on machine learning. As a teacher, I cannot teach any course on. I have to. One has to actually, recap, or one has to do the, take them again to the linear algebra, again to the vector calculus, again probability distribution and optimization at that point. Because the moment I touch that problem, I have to use all these ideas. Automatically, I will be using that. So please understand. So these topics cannot be ignored. That's what the important fundamental tools. What is the foundation of machine learning? So this is the mathematical tools we are using. Okay. So the moment you say machine learning connected to the foundation, what is the foundation of machine learning? Regression. That's what I told you. Dimensionality reduction, density estimation, and classification. One such example is like whatever I have given that. It's basically the supervised learning and it's a classification. It's on classification. So what I'm saying is, this is the foundation of machine learning. The moment you touch the problem, either you use regression, either use dimensionality reduction or density estimation or classification, because these things are on the data. Please understand the table, which is that's what I told you, a data-driven model, and you will be using this regression, dimensional reduction, density estimation, and classification. But in order to do all these things, you need to have a mathematical tool like linear algebra, vector calculus, probability distribution, and optimization. That's what I'm saying. So from the machine learning point of view, these are all important. Regression is important. Dimensionality reduction is important. Density estimation is important. Classification is important. Okay, one of the things you will be using is regression, dimensional reduction, or density estimation, or classification. Not all the things you will be, but backend, linear algebra, vector or vector, there is all these combinations. Okay, fine. Let us. So the moment I go to linear algebra, I'll just quickly go through it because you know it already. But the system of, we will be in the world of solving a system of linear equations, m by n system. In the matrix form, it is given as Ax equal to b. I just have a very important thing. If it is linear algebra, what is the thing I have to basically look at? We will be again and again, on the system of linear equations, on a m by n system. Please understand, not on a n by n system, m by n system. So it is a rectangular system. So then m by n system means we need to know how to invertible. The invertible is the important thing. So you cannot say that if A is invertible, I can write X equal to A inverse. Please understand, I'm not having a square system. I'm having a rectangular system. So if A is not invertible, I can write that X as A transpose A inverse into A transpose B. In a general, I'm just giving you a kind of overview. It's not that I'm trying to teach you what is linear algebra. What is the message here is, in the linear algebra, the main thing, it's a large system. We will be in the world of matrices, and we will be in the world of large linear system. Yeah, in the world of we will be in the solving a large system of rectangular systems. So then I need X. Okay, is it invertible? Is it not invertible? If it is not invertible, what is X? Then do you have any numerical method? A inverse is a heavy computational, it is a heavy task. Inverse, computing the inverse of a matrix is a costly affair. So do you have any iterative method or any numerical method so that the cost of direct A inverse is avoided? That is why in most of the numerical method, most of the softwares what you are using it doing it. So we can do it in a iterative method in this form. So what type of iterative method? Whether that iterative method converges, because you will be using it in your this one. This will be a component. Please understand. It's not the main thing in your machine. This will be a component. We will be doing that. Unless I have a powerful handling the high scale large systems with large rectangular system. How do I do that? So then when you go to linear algebra, then we will be, the data or all these things, whatever we are trying to represent, will be in the world of vectors. Okay, then we need to know something on the the linear algebra, the world of vectors. What is linear independence? What is the linear dependence? What is the basis of what is a vector space? Okay, then what is the basis of a vector space? What is the rank of a matrix? So all these things, it has to be understood. Without that, because even when I'm solving in generality, I'm talking about the linear system of linear equation. I need to worry about. I need to talk in terms of the vector space and the basis and basis of the vector space and the rank of matrix, and in turn then I have a linear independence and linear dependence. Without, see, please, as I told you, you are in the world of data, everything finally represented in the form of matrices. Unless I have a strong base in the matrix theory, in turn linear algebra, then how do I, what are all the concepts I need? What concepts, why? Because this has to be taught from the, not from the mathematical point of view. Please understand, you teach it, but why it is important? It has to be taught because I ultimately everything we will be converting into a coding. So this has to be known. Then what do you mean by linear mapping? So those things, linear system, and we talk about a linear mapping, because all your thing we need to try to, what is a model? The model, the whatever way we try to model, we are capturing in terms of a mathematical function. So when you are capturing in terms of a mathematical function, the mappings are very important. And what do you mean by a linear mapping? I'll show you an example. I'm going to show you an example. And I'm going to give you an idea that how the things are moving. So what do you mean by linear mapping? So when phi is a mapping from a vector v to w, then linear mapping should satisfy this quality. Because whenever I'm representing my data as in terms of a function, I will be using this type of mapping concept. If I don't know what is a linear mapping, then what is a linear manifold? Because the dimension of the problem is unimaginable. So linear manifold, let V be a vector space and x naught belonging to V, which is a vector, and there is a U contained in V. I have a L, which is x naught plus U, defined as x naught for all the set of all x naught plus U, where U belongs to capital U, is called a linear manifold. The very simple problem, what I'm going to show you, I'll be using the linear manifold. We are mapping it because the data is converting as a mathematical function and trying to do some kind of linear manifold. Without knowing what is linear manifold, how do you know that? I started with the system of equation, then I understood that in order to invertible, then I'm using iterative method, then I saw that I need to have some idea about vector spaces, then what is basis, what is the rank of a matrix, then I need to know what is linear dependence or linear independent, then the next case is what is a linear mapping, a linear manifold. All these things has to be thoroughly known, because all these things you are going to do it in your modeling, these are all tools. Then we talk about, as I told you, the error function and all this. What is that? What do you mean by error, and how do you calculate that? It's not one number. It's actually, you should know the norms. So it's a norm is a mapping from V to R, where R is the real line. So V to R, okay, where V is a vector space. So how do you define the norm? Because the x is and if I'm giving a vector, what is the norm of that x? What quality it has to satisfy? What type of norm? Do you have any different norms? You have a L1 norm, you have a L2 norm, you have LP norm, you have L infinity norm. So this is on the vectors. How I am going to do it? When do not have, because I need to, that's what I told you, I need how close it is. How close my information is. How do I find it? Because I am having the information in the form of vectors. Please, the computationally, whenever you go, you have to convert everything in terms of numbers. Some way you have to convert into the number. As you are measuring, as you are mentioning as a number, then based on that, you now try to give corresponding meaning to that. Because all these things has to be captured in mathematically. So without knowing anything about norms, how do I cannot talk about the errors. I cannot talk about the distance between what is that actual one and what is that approximate one. I cannot talk about that. So in what norm? What do you mean by, is it just a norm, and is it what are all the different norms available? Does it satisfy the properties of the metric? So what is the metric? Everyone, you just understand what is the metric? What is the metric? Student learning, what is the metric? What is the metric? Everyone is asking about what is the metric, meaning we need to quantify. We need to quantify. We cannot just like that say, we need to quantify. The moment we need to quantify, we need all this information thoroughly, which is the mathematical. Then trace of a matrix. So what is the properties of the trace of a matrix? So I have to need to talk about norms, properties of linear manifold. What do you mean by linear manifold and properties? Okay. Then I have to talk about the mapping. Then what is that property? So trace of a matrix. Then what is a characteristic polynomial? So what is the eigenvalues? What are the characteristic polynomial? What are the eigenvalue and eigenvectors? I'm not here to teach you, but please understand why I'm telling all this one is these are all important tools. You'll be using it in your suddenly if I take a problem and I'm trying to model, and suddenly I'm using certain eigenvalue. If you do not have any idea about eigenvalue, how do you know that? If I know idea about any eigenvectors, if I do not again talk about a characteristic polynomial, how can you model? Maybe someone has to develop our model, then we try to. But when you are as a this one, all these things will automatically coming up into this one. For example, Google uses the eigenvectors corresponding to the maximum eigenvalue of a matrix to determine the rank of a page for search. So today, whatever you are doing in the Google search, one of the best search engine in the world. Okay, what we are using it every second, every minute we are using it, and without Google search, we are totally arrested under this one. It's a page rank algorithm. Look at that algorithm, how that they have developed. Without mathematics, without this concept, you cannot do that. And searching and according to the location, according to your searches, it tries to give you the best searching research. Okay, so now decomposition, matrix decomposition. One of the best things, Chomsky decomposition. You need to understand because all these things we will be using it. I don't want to, but I'm just giving you the. I'm just recollecting what are all the things we studied in. We don't use any new hyphen, but we need to use all these things in order because you are in the world of data-driven model, meaning you are in the world of matrices. Diagonalizations. Is it a matrix diagonalizable? Why you need that? All your information, whatever I am even for simple cases, because the machine has to learn, as I told, data, model, and learning. The data, model, and learning, please understand, this is the, okay. Then we need to have idea about diagonalization. Is it diagonalizable? What is the advantage of having diagonalization? These are all the linear algebra. Any basic course on linear algebra, we taught this. Now it has to be realized. Okay. Eigen decomposition. The matrix decomposition is one thing, and the eigen decomposition is another thing. So what is the eigen decomposition? Okay. Then you talk about singular value decomposition. It's a very important concept. SVD, singular value decomposition, is a very important concept in machine learning. So this is on the eigen decomposition is for the square matrices. For if we have a rectangular matrix A, then we call it as a singular value decomposition. So what is singular value decomposition? How are you do it in computationally? So what is the comparison between eigen value decomposition and singular value decomposition? So you need to understand. So please, without that, even you cannot touch even a very simple problem on machine learning. Yes, because we are in a position to develop a machine learning algorithm on a, meaning develop a model, in turn a machine learning algorithm for the input, the data driven models. Okay, so because this will tighten up, the mathematical thing will be tighten up. So the way in which it is trained, whatever you are using it for your, for your prediction. So whatever it should be, you are tightening it up. You are measuring it and tightening it up. Everywhere you are trying to tighten up. So that when you take this one onto your unseen data, from the history, you have learned it and developed the model. Now, take in an unseen data and it compares. That's what I told you. It is a decision process. It is a error function and it does it in optimal way. The three core things on machine learning: a decision process, error function, and optimizing the process. So it will tighten up. It automatically checks a metric, it tightens up and says that this is the, okay. So you should understand this concept. Then we go to the vector calculus, derivative of a function. I don't want to now the chain rules and then probability, joint probability, then probability density function, cumulative CDF. So I don't want to now base formula and how are you going to do that, and expected value, that the characterization of the random variables. So then is it a discrete random variable, a continuous random variable? Is it a multivariate random variable? Okay. So once you have a multivariate, then covariance, all these concepts of then basic optimization problem, constraint problem, unconstrained problem, the methodology to solve. So these are all the primal problems. So these are all the minimum topics you need. That's what I listed these topics. It's not that I'm trying to teach you. It's not a one slide I'm trying to teach you. What I'm trying to tell you with this message is you need to have good idea on covariance. You need to have good idea on expected value. You means the characterization of the random variable. Okay. You need to have a good idea on the basic base theorem of base formula. So now optimization, you should know what is the gradient descent algorithm, what is the primal problem, what is the dual problem. Okay, so please understand. These are all I am just highlighted that the tools which is required and the topics which is important on this cases. Okay, there are so many things which you can go in detail, but understand it's course itself. So I want you to basically focus on the how much the depthness, the mathematical depthness is required. That's what I wanted to emphasize. Diagonally, I say all these concepts are very, 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 very important. You must be thorough in multivariate calculus. When I say vector calculus, you must be thorough in multivariate calculus. Directional derivative, gradients, what is that? A line integral, and you are a surface integral. And you have all these things are you are teaching us dimensionality reduction. Please understand. If for example, if I use a vector calculus for a Stokes formula, it is a surface integral into a line integral. Meaning surface integral is of in a three-dimensional space. A surface integral is of a double integral, whereas a line integral is of a one single integral. What about Gauss divergence theorem? It is talking about the volume integral, basically on your volume integral, or third order integral to a second order integral. It's connecting to a surface integral. Only thing that you have to know the intricacies of what is the function you defined on that, what is the typical surface, what is it about? Is it a orientable surface? Is it a non-orientable surface? Because the moment you convert into mathematical way, so that especially in the dimensionality reduction, use this without realizing that its dimensions are reduced. Even a simple Green's formula. Your Green's formula on a plane, right? Stokes formula on a plane is a Green's formula. So your double integral is converted into a line integral. So what do you mean by a line integral? What do you mean by a line in a space? A space curve. So that multivariate calculus is very important. Without that, because we are capturing input. So optimization is very important. Unconstrained, constrained optimization. Go to Mathematica. What is the MATLAB? There is a optimization toolbox which is available to you. It's a super. That means they cover entire of linear. What is the linear programming, non-linear programming, integer programming, 0-1 optimization, whatnot. But you must understand, because the problem, whatever you will be using, you will be using that. So everything has to be. That's what I told you. When you are developing a machine learning algorithm based on this and using the data from the history, from the available collected one, it is learning. So data, and you are developing a model to learn. And all these metrics you are tightening it up. Now it is now ready. Now take that one and applying it on a unseen data, so that whatever it gives you a prediction, it will be a more accurate with less. All these things has to be computed or calculated, and so I need to measure, I need to quantify ultimately. How do I say that this is right? This model gives a right answer. So it has to be done very thorough mathematically, thorough checking, a thorough. I cannot in a loose way, because on the same problem domain. I'm not saying that same problem, unseen data on the same problem domain. For that one, it gives you the prediction. Okay, now let us take a simple problem. With that, I will close this talk. A simple problem. As I told you, it's only overview, but it has to be thoroughly taught, and because we are doing it. We are in fact developing the data, collecting the data on our another model, a problem on a mathematical model through which we collect the data, through which we take the data. The results are given in the form of a table. Then for that taken as a data, and we are using it for our. We are developing over which we are developing a machine learning algorithm for the automation. Then using that machine learning algorithm on the actual problem to understand on an unseen situation. That is the way which we think. Those who are knowing differential equations, for example, and let us take simple one problem. On differential equation, I'm taking. Forget about whether it's connected to some problem which you are modeling as a simple differential equation, along with certain conditions. Ordinary differential equation. If I'm solving the differential equation, or y as a function of, or u as a function of x on a single dimension. Now what I'm doing is the differential equation. This is a model representing this. So then I have a flexibility on my x. So according to that domain, and I collect what is u and collect this as a data. Now using that data, I'm giving it in my machine. I'm trying to understand it from here, because I can apply for different situations, different conditions, because I have a model right away available to me. So that model, mathematical model, first model, which is the differential equation according to the problem, through which I am collecting the data instead of that one, because the model is exactly representing that. But that data, whatever I am collecting this one, using a machine learning, this one, trying to understand what are all the important locations, important points to be, because it gives you some kind of, according to my need, what I'm doing it, I'm putting it in my machine learning. Now what I do is, instead of now using that differential equation, now I go to the machine learning algorithm, applying it on the real. Because the machine learning algorithm works on the data. So I know what data I have to collect it, because this model gives me the correct. So what happened to that? So now for that input, what machine learning algorithm gives as an output, now I can take that one and I can check it in my differential equation, what output gives, I can compare. But what I'm using is, I'm developing a machine learning algorithm based on the data given by this differential equation, and then through which I'm learning, because I have a flexibility of generating the data, through which I'm learning, then the algorithm is used on that. Okay, fine. Now let us take a problem, simple problem. I don't, because it's not a, it should be a, machine learning should be a, you need to have a thorough 1 month crash course on machine learning and the mathematics of it. Mathematical theory, how to apply, the computation is very important, how to convert into everything is important. Without coding, don't talk about any. Let us take a data and model. And I have a name, I have a gender, a degree, a postcode, a age, and annual salaries. So your name, forget about it. Name is not going to play any role, but the gender you have a degree, you have a postcode, you have an age and the annual salary of some person, male or female, depending upon the qualification, depending upon the postcode means where they come from, which location they come from, and according to the ages, what is the annual salary they get. Let it be in terms of pounds, in terms of dollars. Okay. This is you are collecting the data like this. Each one is an example or record. Each column is an attribute. First attribute is a string. Second attribute is gender, again a character. Degree is a character. Postcode is a character. Age is a number. Annual salary is a numeric. But how that system understands? This system can understand only on your algorithm. It has to be converted. In order to have a metric, proper metric, it has to be converted into numbers. So what is the purpose I have the data? So you can ask me, what is the purpose? Okay, you give the data, what should I do? What direction I have to travel? What is the purpose you are giving the data? What direction I have to travel? In order to develop here. So now the gender code, we can convert, name is not going to play a role. So data has to be now gender ID, a +1, -1 for male, +1 for female. Okay. Then degree, depending upon the PhD or these things, I am giving you some number. How it works, I'm talking how you have to think. These numbers, before you put it, you have to add a justification, because later it has to be converted properly. It has to be converted, because what these numbers are going to do in your actual algorithm. Okay. So degree, I am giving you some, if you are a MSc, you have a 2, PhD, you have 3, and a master bachelor, you have 1. And what is the thing? You are giving a postcode. Suppose if I am giving a pin code in India, so I am giving you a pin code of that one, we know the location. Pin code is unique identification, right, of that location. So now that has to be converted into latitude and longitude. I am converting that one into latitude and longitude because I got the data latitude. So I am converting into numbers. Age is a numeric, annual salary is a numeric. Please understand, because all your data, whatever you are collecting, are going to play a crucial role in order what you are planning to travel. So what is that I am looking for? I am looking for at the age of, that is a person who was age 60, what will be the possible salary? Because this guy is coming and asking what will be the right salary I can ask for it. I should not ask less, I should not ask more, or even the industry point of view, they are asking what the salary, if the age is 60, which salary I have to, I can fix it. So that it is not, so that the guy is, it is attractive, the guy is joining, or the company is, you want to, because other things are only you want to fix the salary. So what is the question? Or the 60, this is the data, for 5 data which I have given you. Age, this one, 1, 2, 3, 4, 5. I have put the salary on this one. I have put the salary, and the red dots are the actual salary. I wanted to know for the person of age 60, what is the salary? Is it to be judgeable just by taking age and salary and interpolate? No. Sir, what is the thing? Sir, you have age, you have annual salary. We were taught in our numerical thing. You interpolate 36, 47, and you are having this data. So now you are for 60, you interpolate and you give the, that is the interpolation. So you try to construct a polynomial, interpolation polynomial, and the polynomial passing through all the points. Now you give 60, it will give you the salary. That's not the right one. That's not the right one. That may not be the right one. You have not taken into account what degree he has. You have not taken into account what gender he has. You have not taken into account the location, latitude and longitude. Do you think that if it is a straight mathematical, what is that? If you this one, you simply say that, sir, age and salary, you take it and you just apply 60 and you get the number. No. Just because you never bothered about where they're coming from, what location. Is he working in Chennai or in Chicago? Cannot be the same, right? So what I'm saying is, even if you are converting into this one, what is the latitude, longitude, what degree he has, what is the gender, all these things are playing a crucial role in your model. So that way you just take age and annual salary and computing what is the salary to be given at for the age of 60, or the age of a person of age 60, without taking into all into account, you will be ending up in error. That is a measurement error. Yes, your model is a direct interpolation polynomial. I have 5 points. I construct an interpolation polynomial of degree 4, which is passing through all the points, and I get a function, interpolation function I of x, and I put x equal to 60. I get the number. Do you mean to say that that number is right? Answer is wrong. So we have to take information about that. That's a what type of information we are taking. What way we are going to. So, or linear. I can use linear interpolation, or I can use a linear regression, right? So now the green diagonal line is a linear line. So at the age of 60, you put it this one, you give 100, salary 100. And the prediction x, this is the prediction. They wanted to know the prediction. That's called x equal to 60. What is the predicted this one? This they call it as a prediction through this example. So then they say that you give 100, because my line says that the green line is not an interpolation line. It is basically a linear model for this data. For the data which are 5, this one, the linear model or linear regression line. Because I don't want to use a higher dimensional, higher order, higher degree model, but I want to use the linear model and the linear line, which is representing, meaning the distance between the square of the difference of the sum of the square of the difference of this line and this red bar is minimum. So I have a linear line. Then it suggests that, okay, now at 60, it should be 100. It's not interpolation. Interpolation, I don't know what it gives, but only by taking age and salary. But it really, I'm taking only a linear. I'm taking only this data. I have not taken into account the other information. So this 100, this is the prediction which you are giving 100. Sometimes this guy can ask more, but you would have asked only 100. But he is suggesting, he is using some app, and what will be the right way I can. So is it the right one? Now what we do is, if now what I do is, no, I put this one as along this line, I put this one as my, I say it's a random. So now x equal to 100, what is it? F60 equal to 100. F of 60, whatever f I am linear is 100. I am using it, this is a random variable. So corresponding to this one, I wanted to know, okay? I wanted to put it under, I wanted to put it this along this line. I wanted to have a corresponding to that random variable. Now it is taking a value 100, that is F600. I wanted to treat it as a random variable, and I wanted to try to find out what is the kind of distribution it follows. Based on that, I take a call, because it is basically, we don't know, this is like a random. Linear gives one number, this one gives another number. So I don't take it exactly this one, but I put it like a random variable. The moment I put it as random variable, I need to connect it with then I need to estimate. The moment I put it as a random variable, I need to estimate. According to the information given, I need to estimate what is that. What is the correct estimator? Because I treat it 100, I'm okay. 100 is one thing, but it's not necessary. It is 100 always. It's not necessary that it is 100 is the right one. I need to do the estimate. So in order to make sure this one, then I collect the data. So that's all. For a given data, the maximum likelihood estimate of the parameter result in the green diagonal. So now, according to this one, it gives you the values 125 or something. So if you have accepted 100, you are losing the 25. 100. The prediction is actually should be much higher. 120 plus 130 or something. So this model is basically not from it, it is from your statistical distributions. It has to be converted into that. So that's what I'm using for the given data, the maximum likelihood estimate gives you this. What I mean by then, I have not elaborated, but I'm just giving you one simple problem, how all this has been constructed based on the other information, not only from this data, based on the other information, where location, your gender, everything has been taken into account into your model, because your model becomes multivariate. Then it is suggesting this. Now, another thing, comparing the prediction with the maximum likelihood estimate, that is a green solid line, with the MAP estimate. Okay, green dash line. So now I have another estimate. That gives you even much more than your likelihood estimate. So these two lines, this line is fundamentally a basic age and salary. And take a regression, linear regression field. It tells you 100. Now I don't want to believe this. This is the prediction. I don't want to do that. So what is that machine learning? So learning that's not learning. Learning will not take this way. Learning will put all the possible cases. That's what it is. It is learning from this one. So you treat it as a random variable and try to find out a maximum likelihood estimate for this. Then it tries to put it on a MAP estimate. Then it will try to understand what is that. This is basically, internally it does that. Okay, then we need to understand that this line, whatever we are giving it as a 60, or this is not a deterministic. This model is a probabilistic model. If it is a probabilistic model, what is the random variable and what is the corresponding distribution? And if it is the population comes from here and we need what is the distribution, then if it is a distribution, then it is a parameter. How to estimate the parameter? Based on the parameter estimate, then how your model is basically. Now, what is that kind of prediction? So what I am saying is we have used linear regression. That's what I call it as a curve fitting is one, but linear regression is different. Linear regression is a statistical point of view. That's what I say. Probability distribution statistics are very important. So all these things are dimensionality reduction is important thing. I don't want to now cover all this. This one, it's very important in your modeling. You don't need to take all the things. What is the dimension? How do you reduce the dimension so that computationally it is viable and it has to be calculated in the real time. So what this example, what I wanted to say is the simple example. What I wanted to say is that message is first, whatever you have this data, it has to be converted. It has to be converted into appropriate numbers. These numbers must have a meaning. Then when I want to look at a problem or the age, or what is the aim in which I am trying to go, what is the fixation of the salary according to the age? Okay, then I cannot do it with just a linear line. It has to, the model has to be enhanced. The learning part has to be enhanced in terms of your statistical MAP. So this has to be deep discussion. You have to go into deep discussion and understand. It's not that I just explained the final results. I just put the final results. That's it. But I wanted to explain you that sometimes you will be landing up only with this line. That's wrong. That might be wrong. But you see the results which I am getting it from ML estimate, from that and this one. So how do you are converting that problem into a statistical problem? And how the model is going back. So that's what I want to do. So I don't want to make Bayesian linear regression. Dimensionality reduction is important. Original problem is a D dimension, and the compressed problem is M dimension. And we need to reconstruct the problem to D dimension. So that is a dimensionality reduction, because you cannot use a huge data. What do you mean by dimensionality reduction? That's what, when I say the dimension means how many variables, basically how many columns you have. This is according to this problem. The dimensions are 1, 2, 3, 4, 5. It means 1, 2, 3, 4, 5. There are 6 columns. The dimensionality is minimum 5 to 6. So is it, just imagine when you have huge data, the dimensions of 1,000, million, 1,000. Impossible. What do you mean by dimensional detection? Without knowing what is dimensional detection, what you are doing it in dimensional detection, the data has to be compressed. RD to RM to RD. Reconstructed to RD. So with this side, this is another, what is it? Statistical supervised learning, age, salary, and this is the one, the industry notes, is a classification. They classify it as good or bad. So given this information, your machine learning gives you this result. Your machine learning algorithm, what is the machine learning algorithm? You need to develop the algorithm in such a way that finally, this is the knowledge from this data, which may not be knowing by looking at the data. Okay, but the machine learning algorithm can classify age less than or equal, because B is bad, G is good. So age less than or equal to salary, salary less than or equal to 40, salary greater than or less than or equal to 50. So it is classifies. So it is a supervised learning. So it is learning from this data. This is the learning. So now I am taking a new data, unseen data, where age and salary is given. Now it will judge whether it is going to be a good class or bad class. Based on is good or bad, you take a decision whether to be given or not to be given. But the unseen data, this is the history. From the history, you learn. That's what I'm telling. From the history, you learn. Your machine learning, supervised learning, you learn. Then when you give a new data, it will just tell you that whether G or B. Now you want to know how it is right, how it is correct. That's what I told the error function. Suppose if I am giving a new data, it will tell that you may, according to the new data, according to this learning, you may have to go G. But that means you are taking a decision. How much error it is? What optimal way you are constructing this? That's what I am telling in the decision process. So how you are from this, how you are come to a conclusion that it should be 35, it should be 40, age less than or equal to 35, then split the data, age greater than 35, split the data, you do it in salary here, salary 50 here. How are you going to, who is giving this number? Your machine learning algorithm, your machine learning technique, all these things, that is our purpose. We need to develop this. Then unseen data, we are using it for only age and salary. It will tell you what is that. Then based on that, you take. That's unseen data. This is the seen data. You are already seen and it is learning. Learning and it is giving you. You are developing this algorithm. And the result of the algorithm is this. Imagine you have millions of data, you are only 3 variables in order to show it on the screen. But imagine it's a millions of data, millions of this. What is the thing? You need to, what is the tree building algorithm? So in this machine learning algorithm, the first is the tree building. Tree building has a partition. We need to partition the data. Okay. Then partition the data with the age and making into 2 pieces. Age less than or equal to 35 data goes in one side. Age greater than 35 goes to another side. In that partition, salary less than or equal to 40 go in one direction. Salary greater than 40 goes in another direction. Age greater than 35, salary less than or equal to 50 goes in one piece. Like a cake, you cut the cake. Take the cake and cut it, and every piece has a label, and each label has bad or good. Depending upon bad or good, even when the new entry is coming, you'll know that which is bad and which is good. So who will give this partition data? How are you going to convert this one? Then we need to understand the Gini index. The concept of Gini index, back to break the data. Who is giving? By looking at the data, you don't know. By looking at the even simple data, we don't know this knowledge. So this is a Gini index. Then how do you construct it? How do you take the age and then salary, then this one? So which is the best Gini? According to that, we have to. So how to evaluate the split? How to find that 35? How do you find the 35? What is the split point? Is it a number or is it a category? It has to be converted in number in order to convert. What is that? How are you going to fix this number? So that is called the evaluate split. Before that, what are all the algorithm pre-sorting we need to do that? What is the splitting algorithm? Then how are you update these classes? How are you going to update it from the, these are all learning, please, all algorithms, this I'm learning from the history. And once this is given, this algorithm gives me this one. What I am doing is I am going to do it in a large. I am going to do it for the new unseen data. Unseen data have only age and salary. Unseen data will age and salary. Then it will predict whether it goes to G or B. It is a supervised learning. And that is the purpose of this one. In order to do that, you must understand all your this one. Now we take a benchmark on the database. Australian data set, domain, credit analysis, disease diagnosis, attributes. So Australian, this one, there's a problem is the domain is credit analysis. Attributes are 14. How many classes? 2. Exam 690 exams. Suppose if I go to letter handwriting recognition, attributes are 16 classes. These are all the problems where you the machine learning algorithms are developed. In order to tackle vehicle identification, there are 18 attributes. How many classes you want to classify? 4. How many examples they have taken in order to train, in order to learn? It's not that you have 100, all the 100 you are taking. It is all the 1,000 or all the millions you are taking. You need to take only this many to learn. So here you need only 846 to learn, records to learn. Here in shuttle, space shuttle radiation. So attributes are 9, classes are 7, 57,000 this one. In DNA sequencing, attributes are 180, classes are 3. But how many examples, how many samples you have to take? 3186. What I am saying is, these are all the benchmark data sets, and what is the domain you are talking about? The problem is credit analysis. Another problem domain is disease diagnosis, DNA sequencing, handwriting recognition, language, land usage image, the remote sensing image segmentation, space shuttle radiation, vehicle identification. These are some of the problems where we need the data and we need to learn the data. All these things are how many attributes. This is supervised learning. So one of the interesting book, Mathematics for Machine Learning, is this book, which is available in online. Please have a look. Please read. If some of you are really interested in machine learning algorithm, please. And he has thoroughly covered. He is introducing calculus. He is introducing linear algebra. He is introducing optimization. The first part of the book is a thick book. First part is the entire thing on mathematical tools. Second part is on the foundation of machine learning. So with this, I just gave the overview. Thank you so much for your attention. And at this hour and up to more than one and a half hours, you are sitting and listening. It's a big job. And I must thank you. Thank you so much. If you have any questions, please ask. It's a general overview, showcasing or highlighting or emphasizing the importance of mathematics, and especially linear algebra, and I have shown some examples. And also I have listed some of the problem domains, how many data sets are available, and how many record you need to learn. It's not necessary that all the record you take, okay? So then we need to find the noise in those records, whatever you are measuring. Fine.
Participants, any questions or any queries?
Feel free. So that it's a general overview. That's what I.
If anyone is having any query or any doubt, you can even type in chat box or even unmute yourself.
And open to WS4 while I count from 5 to 0. 5, 4, 3, 2, 1, and 0. On WS4, I want all of you to answer question number 2 and 4. Question number 2
Participants, if anyone is having any doubt, sir, I think they have already started appreciating about the session. Everyone is saying that it's a very informative session. Thank you so much.
Thank you.
Thank you, sir. Thank you so much for making us understand the importance of mathematics for machine learning. And surely we'll all try to motivate our students also to understand the importance of it.
Yes, yes. Okay, thank you.
Thank you so much, sir, for this.
Strengthen your mathematical teaching.
Sure, sir. Sure, sir. Participants, we'll meet again for the next session at 2:15. Sir, are you?
Hello, am
Yes,
I
sir.
audible?
Yes, sir.
Kavita,
Yes, sir.
Dr. Kavita, I am audible? Hello,
Yes, sir. You are audible.
okay. Your voice is very weak. My voice is okay?
Yes, sir. Good afternoon, everyone. I would like to invite our next eminent speaker, Professor Rajiv Agrawal. Dr. Rajiv Agrawal, Director, GL Bajaj Institute of Technology and Management. He has an illustrated experience of more than 27 years in teaching and research. He has delivered many keynote addresses, FDP, faculty analysis, and review in many institutes, universities, and colleges. He has more than 72 publications in reputed international journals and conferences, along with many paper presentations in national conference to his credit. He was a member of BOS MTU Noida, RDC member of MTU Noida and UPTU. Members of Academic Council for the year 2018-2019, AKTU. Convener of one of the BOS member of Governing Council E-Resource Consortium AKTU. Coordinator E-Shoot AKTU ECE Group. He also serves on the advisory board of 2 private universities along with 2 startup companies. He is member of professional bodies such as IEEE, EU India Grid Community, ISTE, and World Academy of Science, Engineering and Technology, and like member of ICEIT. Now I will request Sir to start his session.
So, Dr. Kavita, first of all, thank you for giving such a beautiful introduction. Now, first of all, I'd like to congratulate the Department of Computer Science and Engineering for organizing this FDP ATAL Innovation and also AICT for extending this support to us. And as this conference is located or let's say centered around data sciences, I thought, let's say, I should talk about some of the aspects of the data science which need some entropy measures, which is very important in terms of MB applications. So I'd like to share my slides. So let me know if the slides are visible. My slides are visible?
Not yet, sir.
Okay, just give me one.
Yes, sir, they are visible now.
Now, this is on the. Oh. So, good afternoon to all present in this FDP session. My topic is role of uncertainty measures in data sciences. And these are the content of my lecture, which I'll be delivering. So I'll be first of all talking about the introductions. Second, I'll be talking about origin of the entropy, how entropy is originated. Then I'll be talking about the information aspects of entropy, how uncertainty and entropy concepts are used, how it works, then what is the measure of information, and then useful measures of entropy, which is very effective in case of a data sciences. And I'll take 1 or 2 examples, which will give you insight how entropy estimations will be useful once you are doing any data analysis or once you are using in any data sciences applications. This is the content which I'll be delivering during my session. Now, first of all, starting with the introductions, this entropy is, as you already know, is one of the major key aspect of machine learning. And I think once you are using a machine learning, this concept should be known to everybody. But many times we find that this is complex and the usage of this is limited to more towards the mathematical science rather towards the computer science. So I think that's why I've used a word as perplexes. So many times we find that the usage is limited. Now the growth of the information technology, especially entropy, becomes an important concept in information theory. Now, once we go into a machine learning or a data sciences, this is an important aspect which is considered as information theoretic measures of the uncertainty. And this is used in case of your training data. So whenever you are using a training data, this type of informed theoretic measure is required. And as we know that in case of a data sciences or whenever you are dealing with the data, due to the presence of more than one classes, this theoretical measures will become very important aspect of your applications. Now, this focus of this lecture is to understand the working of entropy by exploring the underlying concept of probability theory, how the formula works, its significance, and why it is important for the data sciences and machine learning. So this is how we'll be talking about your entropy measures and uncertainty. Now, as far as origin of the entropy is concerned, the term entropy was coined by the German physicist and mathematician Rudolf Clausius and was used in the field of initially in the thermodynamics. Then Claude E. Shannon, which is supposed to be a pioneer in case of a communication theory. He's a mathematician and electrical engineer. He's published a paper, a mathematical theory of communication, in which he has used this word, which is called as measure of information, and which is related to choice and uncertainty. So this is how in 1948, the concept of concept of the entropy was initiated by Claude E. Shannon. And Shannon was, as we already know, this is supposed to be a father of information theory, and he has invented the field of information theory. Now, information theory, if I summarize, is a mathematical approach to study of coding of information, along with quantification, storage, communication, and other aspects of information. So that's why information theory nowadays play a very important role, because it deals with all the aspects of applications and the usage which is required in case of information theory, starting from a quantification, storage, and the type of communications we are using. Now, this information entropy was developed as a way to estimate the content of a message. If I say message, I can represent this in terms of information. So I say information. So information can be represented into different form. It can be a message, it can be a signal, it can be a variable. So that's how we say whatever we are sending as in different form, this have some content which we treated this as information. And then whenever we are sending this signal one point to another point, what is the message which we are conveying and how to quantify that message, this become important. So that's why this entropy is a measure of uncertainty, and this is given by any of the form. That's why in case of English meaning of the word entropy, it's a state of disorder. It's a confusion, and it's many times it is also called as disorganization. Now, what is the information? So as we say, let's say information, there is a very broad aspect of information. We get information from any sources. It may be in any form. It may be a variable. We see the value of a variable. If we see the information from a message, if we are using some letter form, so the whatever letter is written that gives you a message, ultimately information. So that's how the information comes, and this measure how to quantify this information. I think this amount of information which is present in all these forms is defined as information entropy. So to summarize, the first important point we have to understand is that the information can be of any form, and if I have to measure the information, I'll be using some measure, and that measure is called as entropy. So this is all about entropy. Now, the amount of information in a message is directly proportional to the amount of surprise. So if I say how the information is related in terms of a mathematical aspect, if I say information is I, so this information I is proportional to a amount of surprise, and this surprise is many times called as uncertainty. So if I say information, the information is directly related to uncertainty, and that's why we have to understand how to capture this uncertainty. Once we capture this uncertainty, then we can quantify the uncertainty in terms of information. Now, transmission of information is associated with the amount of information that we have already discussed. For example, if I am tossing a fair coin, which have two equal outcomes, that is head and tail. So this information, if we say, we already know either it will be head or it will be tail. So that's why we find that the information content in this process or in this event is very less. And the flipping of a coin has a lower entropy because the uncertainty is less, because we already know if I toss a coin, there will be a 1/2 probability that it will be head, or 1/2 probability, or 50% chances it will be head, or 50% chances it will be tail. So that's why we find that the uncertainty in flipping a coin is very less, and that's the information. So we say that the entropy is less. So in information theory, the entropy of a random variable is the average level of information, or if I say information, which is surprise or uncertainty, which is inherent in the variable possible outcomes. So to conclude, in a nutshell, the information is an increase in uncertainty or entropy. So if we find that there is an increase in the uncertainty, that means the information has a greater content, and if it is having a less in uncertainty, that means the information is less, or I can say zero. So this is how information entropy is used in our daily work. Now, what is the meaning of uncertainty? As an engineer, we apply scientific and mathematical principles to design, to manufacture and operate structures, machine, processes, systems, and many other areas. The entire process brings with uncertainty and risk. Means whenever we are doing any of the processes, designing, so there is an uncertainty, hidden uncertainty, which is involved into this process, and as well as risk. We must understand that this uncertainty, if we are to properly account for, so we have to use certain measures, we have to use certain postulate, we have to use certain framework. Now here the question arises that how will be, let's say, quantifying, or how will be putting this uncertainty into a system. Now this uncertainty is defined in terms of two major areas. One is called as aleatory, which related to uncertainty arising due to natural variation in a system. For example, if I say nuclear decay, so in case of a nuclear decay, you do not know what will be the half cycle of this. So that way, this is purely a natural process, and that is depending upon the natural decay and all other aspect of this. And there is another aspect of this, which is called epistemic, and uncertainty due to lack of knowledge about the behavior of a system. So, for example, if I say, if I say earthquake is one of the natural process, but we are capturing this phenomena, or we are capturing this phenomena to give the advance alarms to the people. But we already know that there can be different parameters, there can be different variables. So if you can able to capture all the variables and parameters, then our predictions will be very high. But if we could not able to capture or quantify what are the variable which is affecting the earthquake, then we can understand that our predictions will not be 100%. So that's the uncertainty which is involved into a behavior of a system. So we have to capture this uncertainty into a system. And for this, there are different sources of uncertainty. First of all, there is a data or expert knowledge, means we do not have an exact or expert knowledge which is there. So if we had a sufficient expert knowledge, then we can able to say that the probability or getting this is 100%. So that is again an uncertainty. We are reducing this uncertainty to make it happen. Then knowledge representation, then rule or inferences processes. So that's how the uncertainty comes into system. Same applies to a data sciences. When I'm creating a data, whether we have the uncertainty into a data, whenever we are generating a knowledge representation, whether we have that uncertainty into a data representation, and whenever we are forming any rules or inferences, that also leads to type of uncertainty into a system. So that way, we find that whenever we are doing any of the design, we are using any of the manufacturing or any of the, let's say, processes or a system, the uncertainty is hidden there, and how to capture that uncertainty so that our system should behave like what we accept, what we say. So then this will be a real problem which we have to understand. Now, the question arises that whenever there is an uncertainty into a system or a process, how we should capture this uncertainty. So the answer is we have to quantify this uncertainty using probability. So whenever we have to quantify this, we have to use a probability, and probability is the only rigorous formulations of uncertain knowledge. Now here we have discussed about the information, then we have discussed about entropy, how this entropy is used to measure the information. Then once we say it as an information, this is also related to uncertainty, how this uncertainty generate into a system, and what are the ways by which we can quantify this uncertainty. So that's how at present we have discussed about that. Now, this is a concept of entropy. Now, as we have rightly said in our previous discussion, that entropy is the measure of the information. Now, for example, if I choose these three figures, if a point represents a gas molecule, then which system has the more entropy? So we have to find out, we have to quantify, we have to use entropy postulate to generate what is the average information, what is the highest information, and accordingly, what is the measure. Then, for example, if we have a more order, that means it is less entropy because it is organized, more organized. When it is more organized, that means it has less entropy. Less ordered, higher entropy. More organized, more order, less probable. And less organized or disorder, more probable. So that's how the concept of the entropy is related to the ordered system, is also related to a probability, where we are talking about a less probable or more probable. So that's how we can calculate the entropy in a system. Again, universe, what is its entropy value and its starting point? So this has become a big question, because how you can capture this or quantify the entropy into a system, because this is totally disordered. So means once it is disordered, that means entropy is very high. So how to make this, how to measure it, what is the starting point of using? So this is the open challenge for the scientists and as well as researchers, the how to talk in terms of entropy in case of such a universe. Now, how does entropy actually works? As I have discussed that this is formulated, or this theory was given by Claude Shannon. He had expressed this relationship between the probability and the heterogeneity or impurity in the mathematical form with the help of the following equation. So Hx, if x is a variable, we say that entropy is defined as Hx, which is equal to summation pi log to the base 2 pi. Sorry, I think this is subscript, so it's log to the base 2 pi. Now, the uncertainty or the purity is represented as log to the base 2 of the probability of category pi. The index I refers to the number of possible categories. Here I is equal to 2 because we are talking in terms of a binary classification. But as a general representation, the entropy is given as Hx is equal to minus pi log pi. So if you are using in terms of binary classification or binary representation, I put a log 2, and generally the base can be defined as p log to the base 2 pi. Now, this is very interesting. Here you will be finding that in case of this, whenever I'm plotting this probability, so I say log pi. So if it is log pi, and if I put log pi is equal to 0, the log 0 will lead to 1, right? So here we have to find out that whenever we are relating this probability in terms of entropy, the log pi will have their representation, because in case of this, whenever this is 1, this representation lead to 0, and whenever this is 0.5, it will have a maximum value. But if I put again a log 1, this will have an infinite value. So this will go like this. So what basically we are doing, actually, we are putting a pi in front of log pi so that it can come to this form. Otherwise, what will happen? It will lead to an infinite curve. So to avoid this, we are multiplying this pi. So that's why it is written here, the entropy or the impurity measures can only take value from 0 to 1. As the probability ranges from 0 to 1, hence we do not want that above situation, because it will lead to 1. If you put at log as 1 as log 1, you find it will lead to an infinite type of a situation. To avoid that, to make the curve value log 2 pi back to 0, we multiply log 2 pi with the probability, that is pi itself. That's why this representation is also represented as pi log 2 pi. And as the log value will be minus, to make it positive, because it cannot be negative, there is a minus which is added into a system. So ultimately, this is represented as Hx is equal to minus summation pi log 2 pi. And I think many of the people must know that this is the general framework which is defining your entropy of any system. Now, as far as information measure is concerned, we have already discussed. So that information means how much information is received when we observe a specific value for a discrete random variable. If we are dividing this x and if x as a discrete random representation, that means we are talking in terms of amount of information. Amount of information means a degree of surprise. Certain means no information. If I say sun rises in the east, so everybody knows that there is no uncertainty and this is a static fact. So that means we are not giving any other information. Certain means it is certain that the sun rises in the east. That means it has no information. And same applies to our classes. Then if a teacher goes to a class and if he writes whatever is written on a book, that means he has passed no information to the student, because that information is already available to a student because he can refer a book. So that's why the information is always dealing with the uncertainty. If it is something is certain, we say there is no information because it is there to be certain that this will happen. More information when event is unlikely, means if there is a there is an uncertainty which is leading to a maximum, then we find that there is more information. Means if there is a higher uncertainty, there is a more information. Depends on probability distribution Px, and we quantify Hx. If there are two unrelated events, let us say event X, and we want that H, which is an event of two events X and Y. So this will be Hx plus Hy, and thus we choose that this entropy is minus log 2 PS. Negative is sure the information measure is positive. We have already discussed that. So the average information is transmitted as expected with respect to the probability is referred as entropy, and which is again given in terms of a variable as summation x px log 2 px, where x can take the values from finite values from 1 to n. So this is how we are defining in terms of a information measure, which is used in case of your mostly in communications, where we are finding this aspect. Now, as example, I'll give you one example, which is from a communication side or information theory, that if you are using a uniform distribution, so and we have a random variable which has 8 possible states, and that's why if I find out this Hx or entropy, this will be equal to 3 bits. Means we need 3 bits to transmit this information. But if it is a non-uniform distribution, because if it has X state and if it is not equal likely happen, then there will be a probability of different, let's say, values. And that's why we find that this Hx or the entropy is 2 bits. So you can see that entropy is reduced to 2, whereas in case of the equal likely, it has increased to 3. So the conclusion is that in case of a non-uniform distribution, it has smaller entropy than uniform. Has an interpretation in terms of disorder, means the second terms have more disorder, whereas first has less disorder. So because it is equally likely, that's why the disorder in the first case is less, whereas in second case, the disorder is higher. That's why we find that the entropy measures will be changing. Now, these are some of the aspects which is used specifically in case of a data sciences. And these are the very, very important, what we say, representation, which is widely used in case of a data sciences. I'll give you just a mathematical expression. I do not know how much you are comfortable with it. This is just a simple representation. These below, which I have put it into a blue line, is the conclusion which we have to understand. Now, many times we see the data is represented into a histogram. Now, whenever we see a histogram and we have to relate this in terms of information, so again, the information is to be quantified in terms of entropy. And how you see that what is the level of information and how you find that what is the entropy measure. So that's why I have concluded this, that sharply peaked distribution has low entropy. So means it has low entropy, and distribution spread more evenly will have higher entropy. So that means this, if you are coming to a data which is more distributed, you can understand that it's had higher entropy. Higher entropy means higher disorder. Whereas if there is a low entropy, the data is more aligned. The data is more what we say is ordered. That's why this also give you a direct interpretation whenever you are dealing with the data, that this is more ordered, this is more disordered. So that's how I have simplified the form of entropy and histogram representation, which is widely used in case of your data sciences, that if a data is given to you, which is represented in a histogram form, how to relate ordered and disordered data. The second aspect is maximum entropy configuration. Now, again, the representation, we are talking in terms of a maximized solution, how the entropy can be maximized. This solution is given as H estimated, which is summation Pxi ln Pxi, which is general representation of your, what we say it as a entropy. But here we are talking in terms of a maximum. That's why we have introduced a lambda here, and where they'll be talking in terms of a rest aspect of xi minus 1. So again, the meaning here is whenever you have to calculate the maximum value of entropy, it will be always a natural log of n. To verify this, we have to find out the second order derivative. With those people who are interested, they can use the second derivative. And again, they can find the second derivative by which you can able to know that it will be always represented in terms of ln m. Now, as we move forward, this is again a concept which is used widely in data sciences, that we have first of all talked about the entropy. So if any data is given which is ordered, so we have find out whether this is how the data is ordered, whether it is more ordered, whether it is less ordered. Then we find out what will be the maximum ordered data if you have different classes. In that case, you use a maximum entropy framework by which you can able to find out what is the maximum entropy or what is the level of information which is transmitted in case of these data. Then there is another term which is used, entropy with continuous variable. Whenever we have to find out this entropy of a continuous variable, discrete, we already know, we have to just divide this data into different bins, as we are using in case of a numerical integration. So if it is an integration, let us say 0 to some value, and if we have to find out the numerical integration, so we are dividing this in terms of a different parts, or we are segregating into different bins. The same approach is applied here. Whenever you have to find the entropy with a continuous variable, you have to divide your whole X into different bins, and where the width is taken as delta. So this is how you represent this, and ultimately the representation is same. The only change which we find is that it will be differ by a quantity which is called ln delta, which will again diverge. So this is an important concept which is used, and in case of the continuous variable, whenever you are dealing with the data which is continuous, means you are dealing with the signals, you are dealing with waveform, and where you have to find out some entropy, or you have to see the disorder or order of a particular waveform. So this is a very important tool which can be used or measured, that is known as differential entropy. So whenever you are dealing with this continuous variable, this term is called as a differential entropy. Discrete and continuous form of entropy only differ by quantity ln delta, which ultimately diverge. So this is the genesis of this, that you can use this differential entropy in case of your continuous variable, and that's the difference whenever you are dealing with a discrete event or whenever you are dealing with a continuous event or a continuous data. The difference will be quantified in terms of ln delta. This is used widely in case of a data science. Again, in case of entropy with multiple continuous variable, if you have more than one variable, the differential entropy of multiple continuous variable again represented as an integration px ln px ds. Now, for what distribution is differential entropy maximized? For discrete distribution, it will be uniform. So means if you have an event which is discrete, which is coming discretely, or event is not coming continuous, or your values are not continuous, that means if you maximize it, it will lead to a uniform distribution. Whenever you have a continuous representation or a signal or a waveform, and if you maximize your entropy, it will lead to a Gaussian. So that's again an important aspect which is applicable in case of any form of a data. When you use and you find that some inferences is generated from this data. So these type of a measure are very effective while dealing with the data. Now, maximizing differential entropy. So that's a way how you maximize this. This is a mathematical representation, and ultimately this is just show that how this will lead to a Gaussian representation. So you can see that once I use this, you'll be finding that the differential entropy, if I maximize it, which will lead to a Gaussian type of a representation. And the value of the maximum entropy will be defined as hx 1 by half 1 plus ln 2 pi sigma square. So you can refer any of the, let's say, book where you find that how the value of maximum entropy can be represented. And this is another important aspect, that entropy increases as variance increases. So this is again, you have to understand that once we keep on increasing the variance, we find that the entropy of these data will keep on increasing. So this is how we can apply whenever we use in case of a data science. There is another approach which is used, which is called as conditional entropy. Many ways we have to also find out the conditional entropy. If a value x is already known, if additional information to specify corresponding value of y, that is, we say if some known value is given to you and you find out the entropy of with respect to the known data, then it is represented as a conditional entropy. Like in case of a probability, if I say probability x given y, the same is the case here, probability ln p y given x. So that's how this is represented. And this is widely used in case of, again, data sciences. So the conclusion is the information needed to describe X and Y is given by information needed to describe X plus additional information needed to specify Y given X. So this can be used as HXY is equal to Y given X plus HX, and the opposite form is also possible. That's how you can use these form whenever you are seeing as a conditional entropy, or whenever you are dealing with a conditional data where there is some conditions which is put, and you want some inferences, or you want some let's say order in case of this. So that's way you can use as a conditional entropy in that case. Now again, there is a relative entropy, and this has a wide application, and this is also called as KL divergence, right? And this is a very important concept which is used in case of a Bayesian analysis. Entropy comes from information theory, and KL divergence, which is called as Kullberg-Lieber divergence or related entropy, comes from pattern recognition, since it is a distance. So to how you can use the scale divergence, or you can use this relative entropy. For example, I'll give you just let us say you want to have two patterns. Number one, let us say this is a pattern of a particular waveform 1 and particular waveform 2. So there can be different statistical tests which can be used, but this is a divergence. We want whether this is diverging towards that particular waveform or not, on what is the how accurate or how distance this one waveform is from the other. So if I have to represent this KL divergence, this is basically a distance between two cycles or two waveforms or two signals or two continuous variables. So this is very important aspect whenever we are what we say it as a comparing any of the two waveforms or two data. We find that this KL divergence plays a very important role, by which we can able to understand how much this one waveform deviates from other, or how close is one waveform with the other. So this is how the KL divergence, or a relative, which is called as relative entropy, is used in case of a data sciences. And this is a relative entropy or KL divergence formula. That is KL P divergence to Q means P. There is a variable P. There is a variable Q, and we are saying that P is diverging toward Q. Means we are saying that P is equal to Q, but divergence leading to Q, divergence towards Q. But for simplicity, we can say that we are comparing these two waveform or these two variables, and this is how it is represented. And in a blue, this is the formula that KL P divergence Q is integration Px ln Px divided by Qs ds. So this is how the relative entropy is used, and this is one of the major applications you will find if you go see any of the research paper. You will find that KL divergence is very much used for generating the behavior of two variable or two waveforms. It's not a symmetrical quantity. That is, you cannot say that P divergence into Q is not equal to K Q divergence between. It's quite obvious because two waveforms are different, two variables are different, right? And this is the condition which satisfies the KL divergence or relative entropy. And then this is a major, let's say what we say it as a tool, which is applied in case of a data sciences. Now, this is as a gain. So for modeling the KL divergence of the posterior measure, the amount of information gain expected from query. So you can generate a query that is divergence P theta given X, and we are talking about X dash, how you can use it. The goal is to choose a query that maximizes the KL divergence between posterior and prior. So this is again the same representation where we are saying that you are using a query which maximize or which is the closest towards these two posterior and prior data, right? So this is widely used, as I have discussed, in case of a data science, and you find many of the applications. Another framework or another terminology or another term which is very effectively used in case of data sciences is the mutual information. And again, this mutual information, if I say this is an independent variable, so this in mutual information, so you can find out P x and y ln px dot py pxy dx. This is called a mutual information between variable x and y. So this is again an important aspect which is many times used to find out how these two data are mutually related. So that's why we find what is the mutual information in case of this. Now again, this mutual information, as I have discussed, is using a sum and product rule. The I information xy is entropy hx minus hx entropy x given entropy of y is equal to h entropy of y minus h entropy of y given x. So this is a sum and product rule, which is again widely used whenever you want to calculate the mutual information, any of the waveform or any of the data. And this is again a Bayesian perspective. I think lots of speakers have already talked about the probability framework, wherein the Bayesian perspective or Bayesian formula, Bayesian rules are widely used in case of your data sciences. And this is an extended version where we are talking in terms of entropy. Again, entropy can be defined in terms of probability, and that's how the Bayesian perspectives automatically comes into these frameworks. Now, how the information theory is used in case of a data sciences. Now, that's the point which I want to discuss in front of you, that compute information contained in data using information theoretic measure. Example, entropy, relative entropy, etc. So means if there is some information content and we are using some data and we want some information theoretic measures, we can use this entropy measure, we can use a relative measure, we can use a mutual, what we say is information or mutual entropy. So that's how these concepts can be used whenever you are dealing with a different data, ultimately informations, and you can find out what is entropy, what is relative entropy, what is mutual entropy, which will give you more, what we say it as a insight into your data, and you can very well correlate these different data as a data scientist. Now, key idea: outliers significantly alter the information contained in data sets. Means there will be outlier always available in a data. So that's, you have to find out what are the outliers, and you can take out these outlier data so that your data become more informative, more meaningful. That's how these can be used as a framework where you find the entropy and other aspect of it, which will be definitely gives you the idea what are the outliers and how you can take out these outliers. Detect instances that significantly alter the information content, and many times this is used in case of your security. Many times it is used in terms of a biometrics, where you are talking in terms of a data anomaly. So that can be detected by using these frameworks. Requires an information theoretic measure. Advantage: operate in an unsupervised mode. Challenges: requires an information theoretic measure sensitive enough to detect irregular, induced, and very few outliers. So to just make it very simple, if you had a data, and many times you find, for example, I give you a real example. Many times once we analyze our scores of a student, we see that the scores of the students are not normal, and you want to make it normal. You want to make it as meaningful data. What happens? There will be some students who are getting 0 or who are getting less than 5 marks. Then there will be some students who are getting more than 48 marks. So what is happening here? Whenever you try to normalize this data, this will lead to a what we say it as a form which cannot be normalized. But if you take out these outliers, let us say if I take the first half of it, negative half of it, that is those students who are lying from 0 to 5 marks. And if I take out the data at a higher level, that is those students who are getting more than 48 marks, then taking out these outliers will make my system as a normal process. So that's how you can use these outliers. We are talking about a very, very simple data. In case of a big data, there will be no such instances where you can use it by manual, or you can say by using certain formula. When there is a big data and you're using with a massive data, you need some learning tools, which talks in terms of outliers, and these outliers can only be calculated once you use some information theoretic aspect of it. And this entropy, relative entropy, mutual entropy, discrete entropy, maximum entropy can be these frameworks which can be used to analyze these data and ultimately comes to some inferences which is meaningful and which has some outcome. Now again, this entropy is also used as an information based loss function, where again we are using a KL divergence and we are finding out what is the bit gain about the model. Right now, these are effectively used extended to optimal design algorithm, where we again talking in terms of a posterior and prior divergence, and we maximize these reduction in a model entropy, wherein we reduce the number of bits required to describe a particular distributions, right? So that's how we can use these KL divergence and also in case of a designing of optimal algorithm. So that's why we can reduce the size, how many bits are required to represent these distributions. Then again, must decide how to handle uncertainty about queries, responses, and model parameters. So this is how again this information is used in case of a data science. Now, this is again, I have given you a real example as I have discussed. Let us say this is a real example, a day-to-day example. There are two sheets which is showing the tabulation marks about in a course as shown. Now, which tabulation of marks shows the good performance of the class? How you can measure the same? That's again an aspect for which we are using some statistical tool. We are finding out the average. We are finding out the maximization. We are finding out, let's say, mean, variance, and standard deviation. But ultimately, I think the best way to find out which is a good performance, you can talk in terms of an information theoretic aspect, and you can talk in terms of an entropy. So this is one of the aspects. The measure of information content. People in general are information hungry. Everybody wants to acquire information. How we acquire information from newspaper, from library, from nature, fallows, etc. Things how a crime detector do it now. Do it to know about the crime from crime spot and criminals. He collects the information, and then once it's collect the information, we find out the link between these information and lead to a culprit or lead to the person who has done this crime. So this is how all about the data, how you are relating this data, how you are making this data more meaningful, and what are the inferences we are generating fit. For that, you use certain theoretic aspect, you use certain frameworks. I think entropy measures and capturing the uncertainty is one of the major aspects of any data scientist. Kids are not their parent asking questions. Many times our kids ask the question. In fact, fundamental thing is that we gather information asking questions, and decision tree induction is no exception. So there can be decision. We may note that information gathering may be certainty or uncertainty. So again, whatever information we are getting, that may be certain or it may have uncertainty within the hidden, or what we say it as a hidden uncertainty within our information. Now, for example, guessing a birthday of your classmate, again, it is with uncertainty 1 by 365. So we had 365 days. So if I have to guess a birthday of a particular person or of your classmate, we define with total number of days. Wherever guessing the day of his birthday, it will be 1 by 7. This uncertainty we say varies between 0 to 1, both inclusive. So this is one of the example how we relate information and how we relate entropy and what information we are getting. As another example, a question related to event that eventually or impossibility will be answered with 0 or 1 at uncertainty. That means if it is true, we can say it is yes or 1. If it is false, we say it is 0. Does sun rises in the east? Answer is with geo uncertainty. Means it's certain. So that means there is geo uncertainty, means there is no information whatever we are passing to anybody. Will mother give birth to male boy? Means again you relate this in terms of a tossing of a coin. Either it will be a boy or it will be a girl. So that means we had 1 and by 2 uncertainty. Is there a planet like Earth in the galaxy? We do not know because we have not explored the galaxy as a whole. The answer is with an extreme uncertainty. That means that if I say yes, again uncertainty is there. If I say no, uncertainty is there because you do not know what the galaxy is all about. Now, definition of entropy reframe, how this entropy can be used. Suppose we are taking, there are m distinct objects which we want to identify, and how we can identify these objects. We ask some series of questions. Then, as a data scientist or as a engineer or as a machine learning expert, we have to minimize, we have to optimize our queries. So to let's say identify what is the object, we create a series of yes or no questions. So this can also be represented that how many minimum questions should be asked so that we can reach to a solution or to reach to an answer. So further, we assume that m is an exact power of 2. That is, we are talking in terms of binary representation. Say m is equal to 2n, where n is greater than equal to. Now, definition of entropy. The entropy of a set m distinct value is the minimum number of yes or no questions needed to determine an unknown values from these m possibilities. Means if I say 8, so m is equal to 8. So we say 2 raised to power 3 which is again, so we had 3 such questions. So this is how you can understand how entropy is very effective whenever you are generating any of the queries. Machine learning, in machine learning, you train the data, and once you train the data, if somebody is using your system, you'll be asking certain question. Based on the certain questions, you'll be generating the answer. So that's again depending upon what type of a questions you are asking and what minimum question is to be asked. So that type of framework, you can very well deal with this type of entropy. Now, this is example 1, where you find this entropy calculation is used. How can we calculate the minimum number of questions that is entropy asked? There are 2 approaches. One is called as brute force approach, and another is a clever approach. Now, the example is, let us say we had a city quiz example. Suppose there is a quiz related to guess a city out of 8 cities, which are as follows. And as we have already seen, that if it is M we are 8, the N will lead to 3. So that means we have to ask minimum 3 questions. So the cities are Bangalore, Bhopal, Bhubaneswar. The question is which city is called as a city of joy. So that's how we can go forward. And let us say by brute force approach, we can ask, is it city X? If yes, stop, else ask next. So what we'll do in this approach, we'll keep on changing the cities. So question number 1, 1 city, 2 city, 3 city, and we find, let's say we keep on asking the questions till we reach to an answer. So no need to ask further questions because answer is already known out by the question number 7 because only 1 is left. So if it is asked randomly, each of these probability is equally likely. That means I had 8 cities, I had 8 questions, then probability will be 1. Hence, on the average, we find the entropy 4.375 questions. Mine means we have to ask at least 4 questions to come to a conclusion that it is that city. So this is how the entropy is used whenever you are using in a data science, whenever you are using machine learning. That's how you can create your system. And this is how they represent that you need minimum 4.3 questions to be asked to reach to a particular answer. So that's a example of one of this. There is another approach, clever approach, where we divide in terms of a binary search or a tree representation. In this approach, we divide this list into 2 halves, pose a questions for a half, repeat the same recursively until we get yes answer. For example, here we divide 8 divided by 2, we had 4. So it say, is it Bangalore, Bhopal, Bhubaneswar or Delhi? If is it no, then again we divide this in 4 divided by 2. Again, it will be 2. Is it Madras or Mumbai? Then again, we'd say no. And third question, again 2 divided by 2, we will get 1. Is it Hyderabad? So after this, we said, let's say after asking these 3 questions, we can able to conclude that what will be the answer of this. So you have seen 2 approaches. One is the brute force, where we are asking the questions and then we have generated an entropy that how many minimum questions are required. The answer was 4.3. Here, in case of a clever approach, we are using a binary search where we find, let's say, we need only 3 questions to be answered. So approach 2 is considered to be best strategy because it is very invariably find the answer and will do so with a minimum number of questions on the average than any other strategy. Approach 1 occasionally do better when you are lucky enough. So that's how you can use in terms of a data science. And this is the right applications of the entropy where you can calculate how many numbers are required. So this we have already discussed. There is no coincidence that 8 is equal to 2 raised to the power 3 and minimum number of yes number question needed is 3. If m is equal to 16, so this is how the possibilities are there and you can generate the number of questions which is required as per the data sets. Now, this is again an example where we are talking in terms of a training set. If there are k classes, C1, C2, Ck, and Pi for I is equal to 1 to k, the minimum here is, these are some of the note which we have put it, and the entropy we already know is E, entropy E, or you can say H is equal to minus 9, I is equal to 1 to M, Pi log 2 Pi, and the above formula should be summed over the non-empty classes only. These are some of the conditions. E is always a positive quantity. E takes into minimum values. So this is how some conditions are there, which is to be put before using this training set. Now, this is a training set. You consider this is the medical data shown in the following table with eyesight, estimated, use type, class. So we have a coded form for all values of attribute. And what is the representation of this? This we can see in the next slide, that how the specification of these attributes are as follow. Age we are divided into 3. 1, 2, 3 means if I put it as 1, this is young, like this, age 1, 2, 3, we have already coded this. So for this case, you find 1 is young, 2 is middle age, and 3rd is old age. Same eyesight we have classified into 2 parts, myopia and hypermetropia. So there you can see the eyesight is categorized into 2 parts. Same applies to estimatic, where you have no or yes, and then use type frequentalness. Now there are classes which is ultimately a resultant which we are generating. So one is a contact lens, second is a normal glass, and three is nothing. Now, in this type of a database, we have calculated the entropy of the database, and we find this will be 1.3. Now, the conclusion here is the entropy of a training set implies the number of yes or no questions on the average needed to determine an unknown test to be classified. So this is again another example. We have already seen two examples how this entropy can be used in case of our data. It is very crucial to decide a series of questions about the value of a set of attributes which collectively determine the classification, right? So sometimes it may make one question, sometimes may more, depending upon the questions you have chosen. And this is the example which we have discussed, how the entropy simple formula can be used in case of your data sciences. And we have not extended this in terms of a KL divergence. We have not extended in terms of a mutual entropy or other aspect of it. You can widely see that once these entropy, a simple formula is making a sense in a long, high big data, then what you can understand the other concept will be having the impact. Now, this is another example, entropy conclusion. We shall estimate the entropy of three different scenarios. The event Y is getting caramel latte coffee pouch. The heterogeneity or the impurity formula of two different classes is as follows. Here we have two different classes, means we are finding out case one, coffee flavor, caramel latte, cappuccino, and total the 10 pouch is probability of this. So here you find that the entropy or information, quantifying information, we get 0.88. Here is another case. This value 0.88 is the measurement of uncertainty that the coffee box full of coffee pouches. So we are generating how many pouches you will be getting this, right? And same applies to a case two, the quantity of pouches, the probability, right? And case three, here you find that all the caramel latte is there. There is no cappuccino. So whenever you take a pouch, that means you already, that's quite obvious, certain that you'll get a caramel latte. So that means this uncertainty is zero in this case. So that's why the entropy will be zero. So in case 2 and 3, you can see the entropy is 1 and 0, right? So 1 is because all have the equal chances, respectively 0.5, 0.5, that way it may lead to entropy 1. And 0 respectively in case 3, when we have only one flavor of the coffee pouch, caramel latte, and have removed all the pouches of cappuccino flavor, then the uncertainty of the supply is also completely removed. And therefore said entropy is 0. We can then conclude that the information is 100%, right? So this is how we can relate different aspect of a data sciences by using the entropy measure frameworks in our cases. Now, these are some of the references you can refer. This is a practical machine learning by Daniel Ting. These are the lecture notes. Information theory by Sargur and Ishrini, 4 slides. This is one of the books which you can refer, Element of Information Theory. Anomaly Detection, a tutorial by Arindam Barija et al. This is one of the slides which I have used for NPTEL. And then Uncertainty chapter, Artificial Intelligence Springer 2013. And then the author is Peter Livando. So at the end, thanks from my side. I'm open for any questions.
Participants, if there's any doubt or any query, you can even type in chat box, or you can even unmute yourself. Is there any doubt? Participants, you are open for quiz. Okay, it seems
there is no questions, right?
Yeah, they have already started appreciating the size and presentation in the
right. But I think from my side, this is one of the major area which the data science or the people who are working in machine learning should think of, because whenever you do, yeah, please.
Yeah, there's just one doubt which is
there
in chat box. What is the practical relevance of using entropy in medical sciences?
Let us say, I'll give you a practical example. There are two ECGs which you have as a live data. Let us say one ECG is normal and another ECG is abnormal. Now, it's a time series, what we say it as a data which is coming. And there are some, what's a point which is to be measured as far as practitioner is concerned. Means if I go to a doctor, so doctor will see the pulse, and it is again seeing in terms of a time and amplitude variation, which is used in case of a medical representation, P, Q, R, S, T, U, and V. Now, as an engineer, we do not understand this medical term. That is, what is P, what will be the value of P, Q, R, S, T, U, V. But as an engineer, what I can understand it as a waveform. Now, if I just simply take these two waveform and apply a KL divergence, so you can able to know that whether it is same or not. And if it is diverging, it is not accurate, means the accuracy is less, it is not fitting into a system. That means there is some abnormality which is coming into your waveform. So that's, I think, the best example you can say in terms of any of the pattern, whether it is ECG, whether it is an EMG, whether it is EMG, any of the waveform, if you use these scale divergence, I think you can able to correlate whether this is a normal data or whether it is an abnormal data.
What is the relation between Gini impurity and entropy?
Impurity or disorder, let us say if I say disorder. So disorder means if it is more disorder, that means we say that the entropy is large, right? And if it is ordered, that means entropy is less.
Okay, I think the participants are done with their doubts. Thank you so much, sir, for this informative session on entropy and information measure.
Thank you, Dr. Kavita. Thank you.
Now I accord a welcome to Dr. Rudra Pratap Ojha. He is head planning at GL Bajaj Institute of Technology and Management. He has done his PhD from NIT Durgapur. He has several publications in international journal and conference to his credit. He has been associated with numerous prestigious projects in the past. I now request Dr. R.P. Ojha, sir, to deliver a vote of thanks.
Thank you, Sikha. Good evening to one and all present here. The value of college education is not the learning of many facts, but the training of mind to think. On behalf of GL Bajaj, I feel extremely privileged to proposing the vote of thanks today. I'm sure from the 5 day of FDP, the participant will get a good knowledge about the data science, and this will be very useful for our development as well as the development of the student. This is the new technology which is going to be used everywhere. In these 5 days, you have to find the different speakers who discussed about the data science and how and where to use the data science, how data is important, and the different technology will be used for storing, cleaning, and implementing all these data with the help of models, and how to get the accurate result. And this accurate result will help out for the success of any thoughts which is required for the society, or it may be anywhere. From the bottom of my heart, I would like to thank Sri Pankaj Agrawal sir, Vice Chairman GLB ITM, whose generous support infused confidence in us, and we are able to convert any event into a resounding success. I would like to thank AICT for their generous support, which contributed in the success of this program. I extend my thanks to Dr. Rajiv Agrawal sir, Director, GL Bajaj Institute of Technology and Management, who has been the guiding force behind the planning of this FDP. Sir always help us and motivate to do the new things. It may be related to FDP, conference, and whatever, and they always supported anytime and anywhere. I also extend my thanks to Dr. Sasank Awasthi, Dean Strategy, who blessed with all kind of support to success of this FDP. What sort may fall to thanks Dr. Sanjeev Pipal sir, HOD CSE, who have been mentor and has worked meticulously to organize this FDP. I extend my thanks, a special thanks to the eminent speakers who shared their valuable knowledge with us during this 5-day FTV. I am very thankful to all participants who were excited to enhance their knowledge bank through this FDP. I wholeheartedly would like to express my thanks to all members who are supporting this FDP, Dr. Kavita, Namita, Sikha, Naveen, Bimal, Dr. Upendra, and Anurag, who have contributed in the planning and implementation of this FDP through valuable suggestions. Finally, would like to end my speech with a quote: teachers are only people who lost their sleep for the sake of other children. Thank you once again. Thanks once again, sir, for your valuable presence, Director, sir.
Thank you, Ujaji. So now there is another validatory program which we'll be holding, or it is just a end of our FDP program?
Sir, FDP program has been end, sir. Now
Okay.
there is a quiz is there, sir, and feedback.
Okay, so for the participant.
Yes, sir.
Right. So
Thank you,
this
sir.
is a right. Okay, then good.
Yes, sir. You
So
can
I
leave,
think
sir.
this quiz will be very important for us, and then I think you will be also sharing the feedback form to them, so that they can write it. What is their let's say input regarding this FDP program? And as you rightly said, Dr. Ojha, so we have tried to collect all type of people, starting from industry to practitioners. So from our side, especially from the organizing committee side, they have tried their best to bring all such peoples into a single platform. And as you have to understand, this data science is not to be coupled with any, what we say it as a limited format. So as a data sciences, there will be always in different tools, there will be always in different paradigms, there will be always different models which will be used. And I think nowadays the people are working on that, and every day this data sciences or machine learning is evolving like anything. So the people are using left and right. There are different models, there are different theorems, there are different postulate which is applied in case of this. So I think if we say that by putting these speakers, we have make you understand the data science, we said no. It is just a small initiative which is taken by our college. It's up to you how you devise, how you understand, how you create your knowledge, and how you apply this knowledge into the real world of data science. Right? Then only you can understand what is data science all about. This is a humble, simple step which will only sensitize you, which will aware you about this data sciences. And I expect all the faculty members that this is just a simple initiative by which we create a sensitization among you. Now you can take this lead forward by understanding, by going forward, taking some, let's example, working on the hands-on, then only you can understand the data sciences.
Thank you, sir, for this valuable suggestion, sir. We'll try to implement this, sir.
Right. So please take a feedback, and if anything is there from our side, you think we can improve and we can do better, we'll be always let's say very there to improve. Should I leave, Dr. Ojha?
Yes, sir. You can leave, sir.
Okay. Thank you all the participants for your patience hearing. And if any doubt, any queries there, I'll share. Dr. Ojha will share my email ID. You can just drop a mail. If it is within my purview, I'll definitely answer your questions and definitely answer your queries. With this, I thanks you all for your presence, and have a wonderful day and have a wonderful, let's say, career ahead.
Thank you, sir.
Thank you, sir. All the participants are requested to turn on their camera. After this, you all are requested to turn on your camera for once. After this, we'll be sharing the link for quiz in the chat box as well as here at the Zoom chat. Participants, quiz link has been shared. I'm always doing that which I cannot do in order that I may learn how to do it. A quote by Pablo Picasso. With this aspiration of continuous learning in our lives, I, Shikha Singh, Assistant Professor, GL Bajaj Institute of Technology and Management, thank you all for making this FDP a fruitful event.
कहाँ करना है? ये सिर्फ वहाँ पे करना है जहाँ पे पार्ट वो